Hello fellow sapiens, and welcome to Sleepless Homo. This channel is for you, the curious human who wants science told softly, without noise, without speculation. Just what we know so far, told humbly. If you find yourself valuing this kind of slow storytelling, I invite you to like this video and subscribe. It helps more tired, thoughtful sapiens discover long-form science content like this, and I'd love to hear from you which time and place you're watching from. It's always fascinating to know where these stories are finding you. And one more small thing, if you happen to drift off during one of these chapters, don't worry. I've added timestamps in the description, so tomorrow you can pick up right where you left the story, because this journey, from start to finish, is worth experiencing. And as always, stay curious, stay calm. Now, let's begin. The story of Earth. From fire to oceans, from silence to life. 4.5 billion years ago, the Earth is not yet the Earth. It is an unfinished place, a glowing sphere of molten rock orbiting a young star. What does a planet look like before it becomes a planet? The answer is violence, collisions, fire, endless bombardment. Out of the swirling disk of dust and gas that once surrounded the newborn sun, small rocky bodies slammed into one another. Gravity welded them together, layer upon layer, until the proto-Earth grew heavy enough to hold itself as a single world. This was the Hadean, named after Hades, the Greek god of the underworld. It is a fitting name, for the surface was not yet a crust but a shifting ocean of magma, torn by impacts, restless under a sky of choking gases. We know little directly of this age. The rocks from that time have almost all vanished, recycled into the mantle by billions of years of tectonics. What remains are only whispers, fragments like tiny zircons found in places such as Western Australia. These crystals, older than 4 billion years, suggest that even in the middle of this inferno, there may have been patches of solid crust and even liquid water. Imagine that. Within a world of lava oceans, small islands of stone, raindrops condensing in the upper air, and pools of water forming where the surface briefly cooled. It challenges our imagination, because the Hadean is both hellish and strangely Earth-like at the same time. But one event above all defines this age. Sometime within the first 100 million years of Earth's existence, our world collided with another. The other body is called Theia, a planet the size of Mars. Its orbit crossed ours at the wrong moment, and the impact was catastrophic. Rock vaporized, oceans of magma splashed into space, and the young Earth was shattered. Yet from this destruction came something permanent. The debris gathered into a sphere of its own, a companion that still orbits us today, the Moon. In those early nights it hung impossibly close in the sky, more than 10 times larger than we see it now. Over billions of years it drifted farther out, but in the Hadean it would have loomed enormous and bright over the molten Earth, lighting the hellscape with an eerie glow. That collision changed everything. The spin of the Earth was altered, the tilt of its axis fixed, the tides amplified by a moon so near. Without that impact, life as we know it might never have been possible. It is strange to think that one random collision among countless others created the conditions that shaped our history. We cannot know the full details, but computer models and isotopic chemistry of lunar rocks confirm that this event happened, and that the Moon is part of Earth's body thrown outward and bound again by gravity. The Hadean atmosphere was thick and suffocating. Volcanic gases poured into the sky. Carbon dioxide, nitrogen, water vapour, methane and ammonia. Oxygen was absent. The sun, meanwhile, was dimmer than today, only about 70% as bright. And yet the world was hot, for greenhouse gases trapped what heat there was. A balance of faint light and dense gases created an environment unlike any that followed. It was unstable and it was dangerous, but it was also the cradle in which the next chapters of Earth would be written. Asteroids rained down in the late heavy bombardment, a period that scarred every surface in the inner solar system. We see its record preserved most clearly on the Moon, which lacks plate tectonics, and so keeps its ancient wounds. On Earth, those scars were erased by constant recycling of crust, but we know the bombardment happened here too. Entire oceans would have boiled away after major strikes, only to condense again in long, endless cycles. Life could not have taken hold easily in such conditions, if it had begun at all. And yet, somewhere within this chaos water collected, and the first continents of rock thickened at the surface. To picture this world, imagine not a blue planet but a red-black one. Rivers of lava glowing at the edges, seas of molten rock broken by rafts of cooling crust. Steam clouds towered overhead, lightning storms flickered across the atmosphere, and the air was dense enough to press against your skin like a weight. It is difficult to think of this as the same Earth we know today, and yet it was the same body, the same mass of rock and metal orbiting the sun, waiting for its future to unfold. The inner structure of the Earth also formed during this age. Heavy elements like iron and nickel sank to the centre, creating a dense metallic core. Above it, the mantle churned with convection, driving the restless energy of volcanism. The outer crust was thin and fragile, easily shattered by impacts. But these separations, core, mantle, crust, were essential. They set up the engine that still powers earthquakes, volcanoes, and the movement of continents today. We do not know exactly when the first ocean stabilised. Some models suggest liquid water appeared surprisingly early, within 100 million years after Earth formed. The zircons again hint at this possibility. But whether oceans covered much of the planet or existed only in scattered basins, they were not the oceans of today. They were acidic, filled with dissolved metals and constantly boiled by volcanic heat. Still, they were water, and water would be the medium of all future life. The Hadean was also the time when the building blocks of life may have been delivered. Comets and carbon-rich asteroids carried organic molecules, amino acids, nucleobases, onto the surface. Whether these compounds survived in the heat is uncertain, but the delivery was constant. It is tempting to imagine that the seeds of life were being sown even then, waiting for calmer times. But we must be careful. We do not know. The evidence is sparse, the rocks are gone, and our knowledge is built on models, comparisons, and a few microscopic minerals. This is why we speak humbly. We are not certain, but we have traces, and we do our best to connect them into a story. By the end of the Hadean, around 4 billion years ago, the worst violence was over. The planet had cooled somewhat, the crust had thickened, and the first true geological processes began to shape the surface. The bombardments continued, but with less intensity. The atmosphere remained heavy, the oceans harsh, but stability was slowly taking hold. Earth was becoming a planet rather than a chaotic remnant of collisions. So what does a planet look like before it becomes a planet? It looks like this. A world of fire, of constant destruction and rebuilding, where the very existence of oceans or continents is in question. It looks like a body finding its form, carved by chance collisions and bound by gravity into something lasting. And it leaves us with haunting questions. How did water endure in such a furnace? How early could life have started? And what if Theia had missed its target? What kind of Earth, or no Earth at all, would we have inherited? These are questions without final answers, and perhaps they never will have them. But they remind us of the fragility of our own existence, rooted in events 4.5 billion years past. The Hadean ends with a planet ready to take its next steps. The stage is set for the first whispers of biology, for the cooling oceans, and for the beginnings of something we might eventually call a world. But in this age, Earth was still mostly hell, and the memory of fire would never leave its rocks. Another way to imagine the Hadean is not by what was present, but by what was absent. There were no continents as we know them, no stable weather cycles, no green landscapes, and no blue skies. Without oxygen in the air, there was no ozone layer, which means ultraviolet radiation from the sun bombarded the surface relentlessly. The skies were likely a hazy red or orange, thick with carbon dioxide, sulfur, and ash from volcanoes that erupted without pause. Beneath this atmosphere, the light of the sun would have been dim and distorted, more like the glow of a dying fire than the steady daylight we experience now. In such conditions, it is almost impossible to imagine complex chemistry organising itself, and yet this was the chemical stage upon which everything that followed depended. The role of the magnetic field is another piece of this puzzle. Early in its history, Earth's molten outer core began to generate a dynamo, producing a planetary shield against the solar wind. Without this, the young sun's intense radiation could have stripped away the atmosphere entirely, as it likely did with Mars. The timing of this magnetic protection is still debated, but if it appeared during the Hadean, it would have preserved the thick air that allowed water vapour to condense into liquid. Once again, small differences in timing could have changed everything. Without the magnetic field, we might not have retained our oceans, and without oceans there could have been no life. Scientists sometimes look to other bodies in the solar system for comparisons, because Earth's Hadean surface has been erased. Venus, with its dense carbon dioxide atmosphere and blistering temperatures, may preserve echoes of what Earth could have become had greenhouse gases spiralled out of control. The Moon, barren and scarred, records the impact history of that same era. And Mars, smaller and geologically quieter, shows how quickly a world can lose its protective blanket of air. By comparing these neighbours, we glimpse what Hadean Earth might have been, even if direct evidence is gone. Another subtle consequence of the Theia collision was the tilt of Earth's axis. Today, our planet leans about 23.5 degrees, and that tilt drives the seasons. Without it, climate would be less dynamic, and some regions might have remained frozen deserts while others baked eternally. That small shift, locked in during the giant impact, set up a planet of constant change. It is one more reminder of how fragile the balance is between chaos and habitability. As the Hadean closed, the first hints of stability emerged. The crust was still thin, but it was now thicker than a film of floating rock. The oceans were not permanent, but they endured longer between cataclysms, and above it all the moon pulled at the tides, grinding energy into the seas and stirring them endlessly. The Hadean was not a place for life as we know it, but it was the foundation for everything that followed. In the silence of deep time, a world of fire was cooling into a world of possibility. How do you prove life existed when the rocks barely survived? That is the haunting question of the Yorkean, the stretch of deep time between 4 billion and 3.6 billion years ago. We step out of the Hadean furnace into a world still restless, still young, but beginning to stabilise in ways that allow us to even consider the possibility of life. The scars of violent bombardment were still visible, but less frequent. The crust, though thin and fragile, had begun to harden. Oceans had formed more reliably, no longer evaporating entirely after every catastrophic impact. This was not yet the Earth we would recognise, but it was no longer just a ball of molten stone. It was perhaps a place where chemistry had the time to become biology. The problem is that evidence from this time is almost entirely gone. Plate tectonics and constant resurfacing recycled nearly everything. The oldest surviving pieces of Earth's crust are rare, and when we find them, they are small fragments caught in younger rocks. Most of our inferences come from tiny minerals or altered remnants, which means that every claim is debated, every conclusion fragile. To talk about the Yorkean is to talk about shadows, about signals buried in stone that has been twisted and baked for billions of years. Still, those shadows whisper something remarkable, that life may have started astonishingly early. One of the most intriguing sources of evidence comes from Greenland. In a region called the Isua Greenstone Belt, rocks more than 3.7 billion years old contain chemical signatures that look suspiciously like the byproducts of biological activity. Ratios of carbon isotopes in some of these rocks are lighter than we would expect from purely geological processes, which can indicate that organisms once fractionated the carbon as they metabolized it. In simpler words, the chemistry looks like it may have passed through living cells. This is not proof. It never is in geology that old. But it is a clue, and clues are all we have. Hydrothermal vents are often imagined as the cradle of this earliest life. On the floor of the young oceans, water percolated through cracks in the crust, heated by magma, and erupted back into the sea enriched with minerals. These vents created sharp chemical gradients, and gradients are the currency of metabolism. Life, as we know it, thrives on differences: hot and cold, acidic and alkaline, electron donors and electron acceptors. The Archean oceans may have been filled with such gradients, offering tiny chambers and mineral scaffolds where molecules could assemble into self-replicating structures. Some researchers see these vents not only as places where life could have survived, but where it could have begun. Other hints come from structures that resemble stromatolites, layered mounds built by microbial mats. In rocks from Western Australia and again in Greenland, There are formations dated to nearly 3.7 billion years that some interpret as early stromatolites. These would mean that not only had life appeared by the Eocene, but that it was already forming communities, shaping sediments, and leaving a mark large enough to persist in stone. Critics argue these could be abiotic, formed by chemical precipitation rather than biology. The debate is unresolved. But the fact that the structures look so much like later stromatolites is, at minimum, provocative. The oceans themselves were alien. They were not blue as we know them, but greenish or even murky, rich in dissolved iron and minerals. Without oxygen, iron did not rust and sink but remained in solution, giving the water a metallic character. When microbes later began to produce oxygen, that iron would precipitate out, staining sediments red and leaving the banded iron formations we find today. But in the Eocene, the oceans were a soup of metals, acids, and simple organic molecules. This was the broth in which the first cells lived, if indeed they had emerged by then. Another window into the Eocene comes from the rhythms of day and night. The young Earth still spun faster than it does today. Days were shorter, perhaps as brief as 18 hours. This meant more frequent cycles of light and darkness, tides pulled powerfully by a closer moon, and more opportunities for primitive chemistry to be driven by changing conditions. Imagine being a single molecule in a tide pool, washed by waves under an orange sky, heated and cooled twice as often as today. The pace of the planet itself may have accelerated the pace of prebiotic chemistry. What makes all of this so difficult to pin down is that the rocks themselves do not survive intact. Every sample from this time has been metamorphosed, altered by heat and pressure over billions of years. Signals of biology can be erased or mimicked by purely chemical processes. A lighter ratio of carbon isotopes could be from life, or from volcanic degassing. A layered mound could be a stromatolite, or it could be a purely mineral stack. We are forced to work with imperfect evidence, to weigh probabilities, to remain humble. Scientists argue fiercely about these interpretations because the stakes are so high. If life existed by 3.8 billion years ago, then it appeared almost immediately after the planet cooled. That would suggest life is quick to emerge wherever conditions allow. If not, if the signals are misleading, then perhaps it took far longer, and Earth is more unusual. And so the Eocene leaves us with questions more profound than answers. Was life already here, hidden in microbial mats, consuming chemical energy at vents, leaving isotope fingerprints in ancient carbon? Or are we chasing illusions in rocks too damaged to speak clearly? Either way, what is undeniable is that the stage was ready. Oceans existed, crust had stabilized enough to host sediments, chemical cycles were in place. The Earth had cooled enough that it was no longer only fire, and time itself was beginning to allow complexity to accumulate. By the end of this span, around 3.6 billion years ago, the conditions of habitability were firmly established. Continents were small and scattered, seas were acidic and hot, the air thick and hostile, but the possibility of life was real, and if life had not yet begun, it was about to. That is the power of the Eocene. It marks the edge between a purely geological world and a potentially biological one. The haunting question remains, if life did appear so quickly, then why? Is life an inevitable outcome of chemistry under the right conditions? Or is Earth the rare accident where the improbable happened? We do not yet know. The stones of Greenland, the zircons of Australia, the debates over isotope ratios. These are all we have. Fragments of a story written in a language almost erased. And yet they are enough to tell us this. The Earth of the Eocene was no longer a planet without mercy, but a planet of possibilities. One of the subtle but transformative features of the Eocene was the birth of something like stability in the crust itself. In the Hadean, any land that formed was likely fleeting, broken apart by impacts or swallowed by magma. But during the Eocene, the crust thickened enough to resist constant recycling. The beginnings of proto-continents emerged, small cratonic seeds that would one day grow into the foundations of all modern landmasses. These cratons, remnants such as the Acasta gneiss in Canada, are some of the oldest surviving rocks on Earth, dated at just over 4 billion years. To hold a piece of this stone is to touch the silence of the Eocene itself. These cratons acted like rafts of stability on a restless mantle, and they gave the ocean shallow environments where sediments could accumulate, and where life, if it existed, could cling. In those shallow basins, chemistry and geology intersected in remarkable ways. Sunlight could penetrate through relatively clear waters, creating environments where light-driven reactions could take place. The idea of photosynthesis is often associated with later eras, but the basic capacity to harvest light energy might have roots that extend back into this period. Even if full photosynthesis had not yet appeared, ultraviolet light from the sun could drive reactions among simple organic molecules, feeding the pools of prebiotic chemistry with fresh energy each day. The interplay of sunlight, minerals and water created a planetary laboratory. Meanwhile, tides were relentless. With the moon so much closer, its pull was immense, and the shorter length of Earth's day meant tidal cycles repeated more often. Coastlines would have been dynamic zones, with pools filling and draining rapidly, wetting and drying sediments over and over. These cycles are important because they concentrate molecules, forcing them together in ways that static water does not. A dry phase can cause polymers to form, while a wet phase disperses them, spreading them through the environment. Each tide was, in effect, an experiment repeated endlessly for hundreds of millions of years. Another possibility raised by the Archean record is that life may have found refuge underground. Heat from the interior of the Earth created hydrothermal systems not only on the seafloor but within the crust itself. Water seeping into fractures could interact with minerals at high temperature, producing hydrogen and other reduced compounds that serve as chemical fuel. In such protected environments, shielded from radiation and bombardment, the earliest metabolisms could have taken hold. This perspective widens the picture of habitability. It was not just about surface oceans, but about the chemical factories hidden in rock. What unites all of these possibilities, tide pools, shallow seas, deep hydrothermal fractures, is that the Eoarchean was no longer a planet in chaos. For the first time in Earth's story, conditions persisted long enough for patterns to emerge. Rocks lasted more than a few million years. Oceans did not vanish overnight. Chemistry was not constantly reset by fire. Whether or not life had begun, the planet itself was becoming a platform upon which life could appear. The uncertainty leaves us with a haunting realization. If life was already here, its traces are almost gone. If life was not yet here, then this was the moment before the spark. Either way, the Archean stands as a threshold. It is the difference between a world that merely existed and a world that might have begun to live. Why do microbes leave monuments larger than pyramids? To answer that, we step into the Paleoarchean, between 3.6 and 3.2 billion years ago, a stretch of time when Earth was still far removed from anything familiar, yet already displaying signs that life had not only appeared, but was beginning to leave unmistakable marks on the planet itself. By this stage, the chaos of the Hadean and the fragile balance of the Archean were behind us. The crust was stronger, oceans were no longer temporary, and the bombardments had slowed enough for life to persist if it had already gained a foothold. The question is not only whether life existed, but how it began to shape the surface of the Earth in ways we can still detect today. The most striking evidence from this period comes in the form of stromatolites, layered structures formed by microbial mats. These are not fossils of individual cells. No cell walls survived from billions of years ago. Instead, stromatolites are collective signatures of life, built layer by layer as microbes trapped sediments, secreted sticky films, and grew upward toward sunlight. Over centuries, these mats accumulated into domes, mounds, and columns. Some stromatolites reach several meters in height, larger than any building made by humans until tens of thousands of years ago. They were not created by design or intention, but by persistence, a slow architectural byproduct of microbial life-seeking light. Stromatolites from the Paleoarchean are found in places like the Pilbara Craton of Western Australia and the Barberton Greenstone Belt of South Africa. These regions preserve rocks more than 3 billion years old, and within them are structures that match the morphology of younger, undisputed stromatolites. Layer upon layer of finely laminated stone resembles the accretion of microbial mats, and isotope signatures in the carbon within these layers further suggest biological activity. Critics always raise the possibility that such formations could be abiotic, produced by simple chemical precipitation, but the weight of evidence leans toward biology. If these truly are stromatolites, then we are looking at cities of microbes, organised, self-sustaining communities thriving in shallow seas 3.5 billion years ago. The environments where these mats flourished were likely coastal lagoons and tidal flats. Here sunlight penetrated shallow water, nutrients washed in from volcanic land masses, and tides exposed mats to cycles of wetting and drying. In these marginal zones, microbial mats grew upward, each layer of cells trapping particles and creating a new surface for the next generation. The process was slow but relentless, and over thousands of years the structures became large enough to leave geological traces. To walk across such a shoreline, had anyone existed to do so, would have been to walk on living carpets of microbes, soft at the surface but already turning to stone below. What makes stromatolites so important is that they suggest not only the presence of life, but the organisation of life into cooperative systems. These mats were ecosystems, with microbes sharing resources, cycling nutrients, and layering themselves into functional communities. Some harvested light energy, others metabolized sulfur or iron, and together they stabilize their environment. This is not complexity on the scale of animals or plants, but it is complexity nonetheless. It is the difference between solitary cells drifting in the ocean and vast microbial structures reshaping coastlines. During the Paleoarchean, another transformation may have begun, the dawn of photosynthesis. There is evidence that some microbes had already learned to use sunlight directly as a source of energy. The earliest forms of this process were likely anoxygenic, meaning they did not release oxygen but used other electron donors such as hydrogen sulfide. Still, the principle was revolutionary. To harness light was to tap into the most abundant energy source on the planet. Over time, this innovation would lead to oxygenic photosynthesis, the kind used by cyanobacteria, which would eventually change the atmosphere forever. But even in its earliest forms, photosynthesis expanded the reach of life. Microbes were no longer limited to the scarce chemical gradients of hydrothermal vents or the unstable niches of tide pools. They could spread anywhere light and water were present. The oceans of the Paleoarchean remained different from today's seas. They were warm, perhaps 40 degrees Celsius, and still rich in dissolved iron and other minerals. Without oxygen to rust the iron out of solution, the waters were likely greenish or even reddish. Sunlight filtering through such seas would have created eerie environments for microbes, but to them it was opportunity. They colonized surfaces, built mats, and slowly left their layered monuments behind. If you could dive into a Paleoarchean lagoon, you would not see fish or plants, but carpets of microbes forming bulbous mounds beneath the waves. It would look alien, but it would be alive. Another important development in this time was the continuing growth of continental crust. Protocontinents expanded, giving microbes new surfaces to colonize. Volcanic islands rose from the seas, surrounded by shallow shelves ideal for microbial mats. These growing land masses also changed weathering patterns, delivering new nutrients into the oceans. The interplay between geology and biology was already beginning. Life did not exist apart from Earth. It was woven into its cycles, feeding from them, and in turn altering them. And yet we must remain cautious. Not every layered rock is a stromatolite. Not every carbon isotope signature is proof of biology. The rocks we examine have been altered for billions of years. Heat and pressure distort their textures, and later fluids can overwrite chemical signals. Scientists continue to debate the interpretation of Paleoarchean evidence, and new discoveries can shift consensus. But even with uncertainty, the broad picture is persuasive. Life was here, widespread and active enough to build monuments of stone. By the close of the Paleoarchean, around 3.2 billion years ago, the world was firmly inhabited. Microbes had claimed the shallow seas and left geological records of their presence. Photosynthesis in its primitive forms was underway, setting the stage for the oxygen revolution to come. And the stromatolites, those microbial cities, stood as the earliest known testaments to life's ability to alter a planet. The haunting question that follows is this: if life could build structures on this scale so early, why did it remain microscopic for so long? Why, after billions of years, had it not yet made the leap to larger, more complex forms? That mystery belongs to the chapters ahead. But here, in the Paleoarchean, The stage was set with stone monuments that whispered, life was not only present, it was powerful. Could you survive in oceans hotter than 40 degrees Celsius? That was the condition of Earth during the Mesoarchean, a time stretching from 3.2 to 2.8 billion years ago. To us, it sounds impossible. A modern ocean temperature above 30 degrees already feels extreme, threatening coral reefs and marine life. But in the Mesoarchean, much of the world's seas were more like hot tubs, simmering under a heavy atmosphere, infused with dissolved metals and still roiled by volcanic activity. And yet, life not only survived in these conditions, it expanded and diversified. What was unlivable for us was a flourishing environment for microbes that were adapted to heat, acidity, and chemical extremes. This was a microbial planet, and it was thriving. By this period, the crust of the Earth was thicker and more stable than in earlier ages. Protocontinents grew as volcanic arcs collided and welded together. The seeds of cratons expanded, forming the first large land masses that would endure across deep time. These ancient nuclei are preserved in rocks like those of the Kapval Craton in southern Africa and the Pilbara Craton in Australia. They show evidence that subduction, the process where tectonic plates slide beneath one another, was active. That means Earth had entered a new geological regime. The crust was no longer just breaking and recycling randomly. It was beginning to organise into something like the system of plate tectonics that still moves continents today. This had profound implications for life. Subduction recycles material from the surface back into the mantle and brings up fresh nutrients through volcanism. It also builds mountains and creates new shallow marine shelves where microbes can grow. The beginnings of plate tectonics meant new niches for life, new surfaces to colonise, and constant mixing of chemicals. Though microbes did not know it, the entire planet had become a laboratory, driven by the restless motion of rock deep beneath the surface. The atmosphere was still without oxygen, which means conditions were alien to anything alive today. Gases like methane, carbon dioxide, and nitrogen dominated the sky. In this greenhouse world with the sun dimmer than today, the balance kept the planet hot. The heat of the atmosphere and the heat of the oceans matched, creating a feedback system that kept Earth warmer than we would expect. To modern humans, it would be suffocating, but to ancient microbes it was a steady environment filled with the raw ingredients of metabolism. Evidence for life in this period comes from stromatolites that grew in abundance across the world's shallow seas. These microbial mats did not only exist, they diversified in form, size, and complexity. Some stromatolites show intricate layering patterns, suggesting that microbial communities were experimenting with different ways of trapping sediments and using sunlight. The presence of stromatolites across multiple cratons indicates that life was widespread, not confined to a single corner of the Earth. This was the first global expansion of biology, still microscopic but unmistakably planetary in scale. Microbes were also diversifying metabolically, beyond an oxygenic photosynthesis, which harvested light without producing oxygen. Some microbes exploited sulfur and iron chemistry. In the iron-rich oceans of the Mesoarchean, bacteria metabolized iron compounds, leaving behind chemical traces preserved in banded iron formations. These striped rocks, alternating layers of iron-rich minerals and silica, are among the most striking geological records of this age. Each band marks cycles of microbial activity and geochemical change. To geologists today, they are stone diaries written by microbes that lived nearly 3 billion years ago. The hot oceans may have been stressful for complex chemistry, but they were not barriers for thermophilic organisms. Modern microbes that live in boiling springs or deep-sea vents are considered analogues for these ancient communities. They thrive in conditions that kill other forms of life, using heat and chemical gradients as sources of energy. The Mesoarchean world was dominated by such extremophils. Life adapted not by avoiding extremes but by embracing them. The presence of shallow seas also matters. As protocontinents grew, they created continental shelves and lagoons where sunlight reached the bottom. Here microbial mats thrived, and some scientists argue that these environments encouraged early innovation in photosynthesis. While oxygenic photosynthesis, the kind that releases oxygen, may not yet have been common, precursors to it could have been evolving. Small steps in biochemical pathways may have been tested and refined in these shallow zones. If so, the roots of the Great Oxidation Event lay in these hot Mesoarchean seas, billions of years before oxygen actually accumulated in the atmosphere. Geologically, the Mesoarchean also saw the growth of supercratons, large stable blocks of crust that would later form supercontinents. These included Valbara, a landmass thought to have combined the Kapval and Pilbara cratons. Such continental assemblies would have altered ocean circulation, climate and nutrient cycles. For life, this meant changing coastlines, expanding habitats, and constant shifts in environment. Every geological rearrangement was a biological opportunity. The hot climate and lack of oxygen also meant that ultraviolet radiation from the sun was still intense. Without an ozone layer, surface waters were bombarded by radiation. Microbes had to adapt, perhaps by producing protective pigments, or by hiding in mats where outer layers shielded those beneath. Stromatolites themselves may have been partly defensive structures, with upper microbes sacrificing themselves to absorb radiation, while those below thrived in safer conditions. In this sense, microbial mats were not just cooperative structures, but survival strategies. What is striking about the Mesoarchean is how life and Earth co-evolved. The growth of continents created shallow seas, which hosted stromatolites, which altered sediments and local chemistry. Microbes used iron and sulfur, changing the chemistry of the oceans, which in turn influenced the deposition of minerals. Each side fed back into the other. Life was no longer just present. It was beginning to shape its environment in visible and measurable ways. By the end of the Mesoarchean, around 2.8 billion years ago, Earth was a hot but living world. Oceans boiled with microbial life, stromatolites dotted shorelines, iron layers were laid down across the seabed, and continents were gathering into recognizable landmasses. Oxygen was still absent, multicellular organisms unimaginable, but the biosphere was already global. What began as fragile signals in the Earchean had become a planetary presence. And this leaves us with a haunting question. If life could thrive in oceans hotter than 40 degrees, under skies without oxygen, why did it remain microscopic for so long? For more than 1 billion years it would remain a world of single cells. Perhaps complexity takes extraordinary patience. Or perhaps the conditions of the Mesoarchean were both enabling and limiting, allowing life to spread widely but not yet to evolve beyond the microscopic scale. Either way, this age reminds us that thriving does not always mean changing quickly. Sometimes thriving means enduring in forms so small we cannot see them, but so persistent they can leave monuments larger than pyramids in stone. What happens when life begins to rewrite the atmosphere? That is the story of the Neoarchean, a span of time between 2.8 and 2.5 billion years ago, when microbes began altering the chemistry of Earth in a way that would echo across the rest of planetary history. It was not sudden, nor was it neat. The oxygen that would one day fill our skies and allow animals to breathe first appeared here only in scattered whispers, tiny leaks from microbial metabolism that destabilized an ancient balance. For the first time in Earth's story, biology began to rival geology as a force that could change the face of the planet. In the Mesoarchean, microbial mats had already grown into expansive stromatolites, harnessing sunlight and transforming shallow seas into carpets of living chemistry. By the Neoarchean, some of these microbes had taken photosynthesis a step further. Cyanobacteria, sometimes called blue-green algae, evolved the capacity for oxygenic photosynthesis. Instead of relying on sulfur or iron compounds as electron donors, they split water molecules. The byproduct of this reaction was oxygen gas, released into the surrounding environment. This single biochemical leap, born in mats of simple cells, introduced a new gas into a world that had never known it. At first, the oxygen was absorbed immediately. The oceans of the Neoarchean were filled with dissolved iron and other reduced compounds eager to react. Every molecule of oxygen produced by cyanobacteria quickly oxidized something else. The result was the formation of iron oxides that sank to the seafloor, creating the first great pulses of banded iron formations. These deposits, alternating layers of red hematite and grey silica, are found across the world today in places like Western Australia, South Africa, and North America. They are mined for steel. yet their origin lies in the metabolism of microbes more than 2.5 billion years old. Each band is a record of biological oxygen, meeting geological chemistry, a dialogue written in stone between life and the planet. The release of oxygen, even in trace amounts, had other consequences. Some chemical pathways that had been stable for hundreds of millions of years were suddenly disrupted. Methane, a potent greenhouse gas that helped keep the planet warm under a faint young sun, was broken down by oxygen into carbon dioxide and water. This weakened the greenhouse effect. It would take millions of years for this shift to have climatic consequences, but the seeds of planetary cooling were already being sown. In this way, cyanobacteria were not just changing the air, they were altering the climate system itself. Life also diversified metabolically in response to the oxygen trickling into the environment. Some microbes evolved new enzymes to deal with oxygen's reactive power. What was poison to one cell could be fuel to another. Oxygen is a dangerous molecule, capable of damaging proteins and DNA, but it also carries enormous energetic potential when harnessed correctly. Slowly, new pathways of respiration began to appear. They were primitive in the Neo-Archean, but they hinted at the future, when oxygen would support the vast metabolic demands of multicellular organisms. The evidence for cyanobacteria in this period comes from both morphology and geochemistry. Fossilized stromatolites become more abundant and complex in the Neo-Archean, suggesting microbial communities were flourishing. Microfossils resembling cyanobacteria have been reported in rocks from this time, though their interpretation is debated. More secure is the geochemical record, isotopic signals of carbon that point to photosynthesis, and the iron deposits that point to oxidation. Together, these records make a persuasive case that cyanobacteria were already widespread by the end of the Archean. The continents themselves were also growing. Cratons stabilized and assembled into larger land masses, changing ocean circulation and nutrient delivery. Weathering of these expanding continents washed phosphorus and other key nutrients into the seas, fertilizing microbial growth. The combination of nutrient supply, shallow shelf environments, and evolutionary innovation created a planetary bloom. Cyanobacteria spread across lagoons and continental margins, carpeting vast areas with mats that pumped oxygen into the water day after day. The Neo-Archean also provides evidence for more advanced tectonic activity. Subduction zones grew more complex, and mountain-building events reshaped crustal blocks. With them came volcanic eruptions that belched gases into the air, sometimes reinforcing greenhouse warming and sometimes counteracting the subtle cooling caused by methane loss. It was a tug-of-war between biology and geology, with Earth's climate hanging in the balance. What is humbling is that all of this unfolded invisibly. If you had stood on a shoreline in the Neo-Archean, you would not have seen dramatic changes. The sky was still hazy, perhaps orange or red. The air was still unbreathable, filled with nitrogen, carbon dioxide, and methane. Oxygen was present only in local plumes near microbial mats. The seas were still iron-rich and greenish. To the naked eye, it was still a hostile planet. Yet at the microscopic level, the revolution was underway. Simple cells were carrying out reactions that would eventually shift the composition of the entire atmosphere. The question of why oxygen emerged here and not earlier remains open. Was it simply evolutionary chance, a mutation in a photosynthetic pathway that happened to succeed? Or was it triggered by geological change, such as new nutrient supplies or tectonic upheaval? We do not know. The rocks speak only in fragments, and the biology of microbes leaves little direct fossil record. But the correlation of stromatolite expansion, iron deposition, and geochemical signals suggest that something fundamental had changed in this window of time. By the close of the Neo-Archean, around 2.5 billion years ago, the stage was set for the great oxidation event of the Paleoproterozoic. Oxygen had been leaking into the environment for tens of millions of years, saturating the oceans with iron oxides, slowly building up in localized atmospheres. The Earth was about to cross a threshold. For the first time, free oxygen would accumulate in the air, transforming climate, chemistry, and evolution. The haunting question is whether life knew what it was doing. Of course, it did not. Cyanobacteria did not plan to terraform the planet. They were simply harvesting energy in the most efficient way available, splitting water and releasing a byproduct. Yet that byproduct changed everything. The Neo-Archean is a reminder that profound shifts in Earth history can arise from organisms with no consciousness, no foresight, only chemistry. Life does not act with intention, but its consequences can be planetary. How does invisible gas freeze a planet solid? That is the paradox of the Siderean, a span between 2.5 and 2.3 billion years ago, when oxygen first accumulated in Earth's atmosphere. For nearly 2 billion years, life had existed quietly, consuming chemical gradients and later experimenting with light. It left only subtle marks, traces in isotopes, faint layers in stone. But in the Siderean, life's waste product became a planetary force. Oxygen seeped into the oceans, then into the air, and as it did, it dismantled the greenhouse world that had kept Earth warm under a dim sun. The result was not comfort or flourishing, but one of the first great planetary crises, a freezing Earth, a world locked in ice. The story begins with cyanobacteria. By the late Archean, they had already spread across shallow seas, harvesting sunlight and splitting water molecules for energy. Their innovation was elegant but dangerous. For every reaction that produced carbohydrates, a molecule of oxygen was released. At first, this oxygen did not last long. It reacted with dissolved iron in the oceans, precipitating as oxides that sank to the seafloor. This chemical duel created the vast banded iron formation still mined today. For millions of years, the oceans acted as a sponge, absorbing every breath of oxygen life could exhale. By the start of the Siderean, however, that sponge was saturated. The iron was mostly oxidized. There was nowhere left for oxygen to hide. Gradually, it began to accumulate in the water column and eventually leaked into the atmosphere. For the first time in Earth's history, free oxygen gas lingered in the air. The great oxidation event had begun. To us, oxygen is life. To the organisms of that world, oxygen was poison. The earliest microbes had evolved in an anoxic planet. Their metabolisms depended on reduced gases, and oxygen was a reactive threat that damaged proteins, lipids, and DNA. As oxygen spread, entire lineages of anaerobic organisms were driven into extinction, or forced into marginal environments where oxygen could not reach. Deep sediments, hydrothermal vents, or underground refuges. It was the first global biological catastrophe, not caused by asteroids or volcanism, but by the success of life itself. The atmosphere transformed. Methane, which had been a potent greenhouse gas sustaining warmth under a fainter sun, reacted quickly with the rising oxygen. The chemical reaction turned methane into carbon dioxide and water. Carbon dioxide is still a greenhouse gas, but it is far weaker molecule for molecule than methane. The greenhouse effect diminished sharply, and Earth began to cool. For a planet that received only about 85% of today's solar output, this shift was critical. The warmth that had allowed liquid water to persist slipped away, and ice advanced. Geological evidence suggests that during the Paleoproterozoic, Earth experienced global or near-global glaciations, perhaps the first true Snowball Earth events. Glacial deposits appear on multiple continents at paleolatitudes that suggest ice reached the equator. Drop stones, large rocks carried by icebergs and released into marine sediments as the ice melted, appear in strata that date to this time. These features cannot be explained by local or regional cooling alone. They point to a world where oceans froze over, continents were covered in ice sheets, and the planet as a whole entered a deep freeze. The vision of a Snowball Earth is stark. Imagine oceans capped by kilometers of ice, reflecting sunlight back into space, reinforcing the cold. Volcanoes still erupted, but their gases were trapped beneath the ice or scavenged by weathering. Photosynthetic life near the surface was starved of light, yet life did not die. Microbes survived in cracks, in hydrothermal vents, in refuges beneath the ice where liquid water remained. It was not a planet without life, but a planet where life was forced into the margins. Survival required resilience, and resilience left its mark in the lineages that endured. The Siderean also reminds us how intimately climate is tied to atmospheric chemistry. Small changes in gas concentrations can tip a world from warm to frozen. Oxygen, invisible and odourless, was enough to overturn the balance. We often think of gases as passive, but in deep time they act as agents of transformation. What is waste for one species becomes catastrophe for another. What cools a planet in one context may heat it in another. The evidence for this atmospheric transformation is layered in stone. In sediments older than 2.5 billion years, we find mass-independent fractionation of sulfur isotopes, a signature that can only occur when the atmosphere lacks oxygen. After the Great Oxidation Event, this signal disappears, replaced by patterns consistent with an oxygenated sky. It is a chemical fingerprint of a world that crossed a threshold. The rocks do not give us photographs, but they give us enough to trace the arc of transformation. The human mind struggles with the scale of this change. The Siderian was not a few centuries of crisis, nor a single bad season. It was tens of millions of years in which Earth reeled from a shift in its fundamental chemistry. Entire ecosystems collapsed. New ones arose. The balance between geology and biology tilted forever, and in the end the world emerged colder, more oxidized, and ready for new evolutionary possibilities. Yet the haunting question remains, why here, why then? Why did cyanobacteria evolve oxygenic photosynthesis in the first place? And why did it succeed so thoroughly in this window of time? Was it the availability of nutrients stirred by tectonics and continental growth? Was it random innovation, a mutation that conferred advantage only because conditions allowed it? Or was it inevitable, the only path life could take once it learned to use water as an electron donor? We cannot say for certain. The record is too fragmentary. We are left with models and clues, each pointing to a world on the edge of change. By the end of the Siderian, around 2.3 billion years ago, Earth was permanently altered. Oxygen was no longer a local byproduct, it was a planetary component. The biosphere was reduced in diversity but primed for future innovation. The climate had swung into extremes, forcing life to adapt, and the chemistry of the oceans and the atmosphere had been rewritten. The Great Oxidation Event did not end in this period. It continued to fluctuate for hundreds of millions of years, but here is where the story began. How does invisible gas freeze a planet solid? By being too successful, by tipping the scales of climate in ways no cell could ever intend. It is a reminder that life is not always gentle. Sometimes life changes the world so violently that survival becomes almost impossible. And yet, from that near catastrophe, the Earth of the future was born. Another aspect of the Siderian worth considering is how oxygen reshaped the chemistry of Earth's crust and minerals themselves. Before oxygen began to accumulate, many elements behaved differently. Uranium, for example, remained relatively immobile in reduced conditions, locked away in minerals that barely dissolved. With oxygen present, uranium became soluble, moving into water systems and later concentrating in deposits. This shift not only transformed geochemical cycles, but would much later play a role in how humans could mine and use uranium. The same story holds for other metals, including copper and molybdenum, which became more available in surface environments once oxygen levels began to rise. In this way, the Great Oxidation Event was not only about air and climate, it was also about rewriting the availability of nutrients and resources that future life would depend on. Another subtle transformation was the loss of greenhouse warmth, not just because methane was destroyed, but because weathering of newly exposed continental rocks drew down carbon dioxide. As continents grew larger in the late Archean and early Proterozoic, more land surface was exposed to rain and chemical breakdown. Oxygen accelerated this weathering, binding carbon into carbonate rocks and reducing the amount left in the atmosphere. The combined effect was powerful. Less methane, less carbon dioxide, more reflectivity from expanding ice, and a sun still fainter than today. Earth may have hovered near the edge of permanent glaciation. The fact that it emerged from these icy intervals at all is testimony to the long, slow build-up of volcanic carbon dioxide, released relentlessly by the interior no matter how much was locked away at the surface. The Siderian also gives us one of the earliest examples of ecological feedback loops. Cyanobacteria thrived in shallow seas, produced oxygen, and in doing so poisoned competitors. The death of those competitors cleared more space for cyanobacteria, which spread even further, releasing more oxygen. The cycle reinforced itself until the atmosphere tipped. It is a lesson about how small, local changes can amplify to planetary scales when feedbacks align. Nothing about this was intentional. The microbes were not aiming for domination. Yet through chemistry alone they drove a cascade that changed the entire biosphere. Some scientists have suggested that this oxygenation may have triggered the first significant pulses of biological innovation. Surviving microbes were forced to evolve new strategies: enzymes to detoxify reactive oxygen, pigments to absorb ultraviolet radiation now altered by the growing ozone layer, and perhaps even primitive aerobic respiration. These changes were not immediately transformative, but they planted seeds. Later lineages would refine these pathways into powerful tools, but the initial adaptation may have happened here, in the crucible of the Siderian. In the end, the Siderian represents a threshold moment. Before it, life existed entirely within a reducing world. After it, life faced an oxidizing environment that demanded new solutions. The evidence is written not only in banded iron and sulfur isotopes, but also in the very architecture of the planet. Minerals stabilized only in the presence of oxygen appear for the first time in the rock record at this time. It is as though the entire Earth mineralogy shifted to a new chapter, expanding the palette of stones that could exist. Oxygen did not simply fill the air, it sculpted the very matter beneath our feet. How do volcanoes thaw a frozen world? That is the story of the Rhyatian, a stretch of Earth's history between 2.3 and 2.05 billion years ago. The Siderian had ended with catastrophe, the rise of oxygen, stripping methane from the skies and plunging Earth into one of its deepest freezes. Ice crept toward the equator, oceans sealed over, a world that had been hot with greenhouse gases became pale and cold. Life did not vanish, but it was pressed into refuges, surviving in cracks, vents, and sheltered seas beneath the ice. The Rhyatian is the tale of how that icy grip was broken, how fire from the interior fought back against the frozen surface, and how the chemistry of oceans and air adjusted to the new oxygenated reality. The evidence for this ancient glaciation is scattered but compelling. Sedimentary rocks from Canada, South Africa, and elsewhere contain tillites, conglomerates of stones dropped by glaciers into fine sediments, and dropstones that tell of icebergs drifting into what were once equatorial seas. These deposits lie alongside chemical signatures of a newly oxygenated atmosphere. The connection is hard to ignore. Oxygen rose, methane fell, greenhouse warmth collapsed, and Earth froze. But glaciations do not last forever. Something thawed the world, and in the Rhyatian the main suspect is volcanism. Volcanoes are relentless engines. Even when continents are locked in ice, magma rises from the mantle, carrying with it carbon dioxide and sulfur gases. Carbon dioxide, unlike methane, is a weaker greenhouse gas, but it is still effective when allowed to accumulate. During glaciations, weathering of rocks slows dramatically. Normally chemical weathering consumes carbon dioxide, locking it into carbonate rocks. But when the continents are sealed under kilometres of ice, weathering halts. Volcanoes continue to exhale carbon dioxide unchecked, and over millions of years the concentration in the atmosphere builds. Eventually enough accumulates to overwhelm the cooling feedback of the ice, trapping heat and starting a slow thaw. In the Rhyatian, this process likely repeated more than once. The record suggests a series of glaciations and interglacial thaws, as oxygen levels rose unevenly and volcanic gases cycle between build-up and drawdown. Each thaw would have released torrents of meltwater into the oceans, carrying with it freshly eroded minerals, trace metals and nutrients. The chemistry of the seas changed violently. Oxygenated surface waters mixed with deep anoxic reservoirs rich in dissolved iron and sulfur. The result was pulses of chemical precipitation, iron formations, sulfur minerals, and other deposits that record the instability of the oceans. These chemical shifts were toxic to many organisms, particularly those adapted to stable anoxic conditions. But at the same time, they opened ecological niches for lineages capable of tolerating or exploiting the new chemistry. The Rhyatian oceans were neither uniform nor stable. They were stratified, with oxygenated layers on top and anoxic depths below. The mixing of these layers during glacial melt events could have released clouds of hydrogen sulfide, a gas poisonous to nearly all forms of life. Episodes of eugonia, sulfidic conditions in the oceans, may have stressed surviving microbes, forcing further adaptation. It is a reminder that the Great Oxidation was not a single step, but a drawn-out series of upheavals, with each pulse of oxygen producing both opportunities and crises. Continental growth also played a role in this dynamic. During the Rhyation, large continental blocks such as the Supercraton Canorland were assembling. These growing land masses altered patterns of weathering and ocean circulation. Their assembly may have helped deliver phosphorus into the seas, fertilizing microbial growth and reinforcing cycles of productivity and oxygen release. But larger continents also meant more ice sheets during glaciations, further reflecting sunlight and deepening freezes. The tug-of-war between biology, geology and climate was constant, and Earth oscillated between frozen and thawed states. Life during this time was microscopic, but not passive. Cyanobacteria continued to spread, pumping out oxygen even as it triggered planetary crises. Other microbes clung to anoxic niches, metabolizing sulfur and iron in the shadows of their oxygen-producing cousins. The ecological pressure was intense. Many anaerobic lineages likely perished or retreated permanently into extreme environments where oxygen could not penetrate. Yet this adversity may have spurred innovation. Some researchers suggest that the origins of aerobic respiration, using oxygen to efficiently extract energy from organic molecules, emerged under these conditions. If so, then the struggle to survive oxygen's toxicity gave rise to one of the most powerful metabolisms life has ever invented. The glacial episodes of the Rhyation also remind us how fragile planetary climates can be. A change in atmospheric gases, driven by microbes too small to see, was enough to plunge Earth into ice. Volcanoes hidden deep in the crust were enough to thaw it again. The balance between freezing and thawing was not a contest between equals, but a dance of feedback loops, each tipping the planet one way or the other. To imagine this is to realise how thin the margin of habitability can be. By the close of the Rhyation, around 2.05 billion years ago, Earth had emerged from its first great ice ages. Oxygen was now a permanent part of the atmosphere, though levels fluctuated wildly. The climate was unstable, the oceans chemically restless, but the trajectory was set. The planet had crossed into a new regime where biology and atmosphere were forever entangled. Life had begun to reshape not just its environment, but the climate system itself. The haunting question left by the Rhyation is whether these freezes nearly extinguished life altogether. Did the snowball conditions drive biology to the brink, leaving only scattered survivors in vents and fractures? Or was life never truly at risk, finding abundant refugees beneath the ice? We do not know. The rocks are ambiguous. They preserve traces of glaciers and oceans, isotopes and minerals, but they do not tell us whether the biosphere was thriving or gasping. What is clear is that from this crucible life continued. Fire fought ice, and Earth emerged altered but alive. What happens when the sky falls? To answer this, we step into the Orosirian between 2.05 and 1.8 billion years ago, an age when Earth was struck by one of the greatest impacts in its history, and when continents collided to raise mountain belts that would endure for eons. The Siderian and Rhyasian had left the world altered, with oxygen a permanent feature of the atmosphere and glaciations showing the fragile balance of climate. By the Orosirian, Earth's surface was reshaped by forces both cosmic and internal, giant meteorites falling from the sky and tectonic plates grinding against each other. The most dramatic of these events was the Vredefort impact. Around 2.02 billion years ago, a massive asteroid or protoplanetary fragment slammed into what is now South Africa. Estimates suggest it was at least 10 kilometres across, perhaps larger. The energy released was orders of magnitude beyond any volcanic eruption or earthquake. The impact excavated a crater almost 300 kilometres wide, though erosion and tectonics have since buried and warped its original shape. What remains is the Vredefort Dome, a geological scar that still ranks as the largest verified impact structure on Earth. To imagine this event is almost impossible. A fireball brighter than the sun, shockwaves tearing through crust, tsunamis sweeping across oceans, and ejecta raining down around the globe. Entire regions would have been incinerated instantly, while others were buried under debris and molten rock. The atmosphere would have filled with dust, aerosols, and perhaps even vaporized ocean water. Climate may have swung wildly in the aftermath, cooling as sunlight was blocked, then heating as greenhouse gases accumulated. For microbes already adapting to an oxygenated and unstable world, this was yet another crisis layered onto the others. But impacts are not only destructive, they stir the crust, redistribute materials, and create hydrothermal systems as fractured rocks interact with circulating water. Some researchers suggest that the Vredefort impact may have generated vast hydrothermal networks that persisted for millions of years, offering refugees and chemical playgrounds for microbial communities. In this way, catastrophe also created opportunity. Life's resilience is measured not only in its ability to survive, but in its talent for exploiting the niches disasters leave behind. Beyond the sky's fury, the Orosirian was also a time of tectonic drama. Continents, which had been forming and stabilizing throughout the Archean and Paleoproterozoic, began colliding in earnest. The assembly of supercratons produced mountain belts on scales never seen before. In North America, the trans-Hudson orogeny stitched together large portions of the continent. In other regions, such as West Africa, India, and South America, similar collisions were underway. These orogenies created the first true mountain chains of global scale, precursors to ranges like the Himalayas that would rise billions of years later. The building of mountains had profound consequences for the surface environment. Elevated terrains weather rapidly, delivering nutrients into rivers and oceans. Phosphorus and other minerals washed off the rising highlands, fertilizing microbial life in shallow seas. At the same time, mountain building sequestered carbon dioxide as weathered rocks bound carbon into sediments. This interplay of uplift, weathering and climate became a repeating theme in Earth's history. In the Orosirian, we see one of the earliest full expressions of this cycle. The continents themselves, now larger and more stable, began to assemble into recognizable supercontinents. While the details are debated, configurations such as the proto-supercontinent Columbia may have been emerging in this window of time. If so, then Earth had entered a new tectonic phase where continents drifted, collided, and fused in cycles of supercontinent assembly and breakup. This cycle would dominate the planet's geological story for the next 2 billion years. For life, the Orosirian was a period of adjustment. Oxygen levels were rising but unstable. Oceans oscillated between oxygenated and anoxic conditions, and impacts and tectonics created bursts of environmental change. Microbial ecosystems adapted to shifting chemistries, diversifying into lineages that could tolerate oxygen, and others that retreated to anoxic refuges. The evidence of this adaptation lies in the isotopic record, where signals of carbon and sulfur show swings between oxygen-rich and oxygen-poor environments. It is humbling to consider how little we know of biology in this time. Fossils are scarce, limited mostly to stromatolites and microstructures in rocks. We infer the diversity of metabolisms from chemical signatures rather than preserved organisms. Yet even with limited evidence, the picture is clear enough. Life was not static. It was experimenting, diversifying, and enduring through crises. The Orosirian was not a quiet pause, but a crucible in which life and geology reshaped one another. By the close of the Orosirian, around 1.8 billion years ago, Earth had been permanently marked. The Vredefort structure remained as a scar, mountain belts stretched across continents, and oxygen was a permanent if fluctuating feature of the atmosphere. The climate was less volatile than in the Rhyatian, but instability lingered. The Earth had entered a new equilibrium, with continents, mountains, impacts, and biology entangled in feedbacks that would persist ever after. What happens when the sky falls? It shatters landscapes, reshapes climates, and threatens life. But it also leaves behind new possibilities. The Orosirian reminds us that catastrophe and creation are not opposites in deep time. They are partners, each driving the next stage of change. The haunting question is not how Earth survived such impacts and upheavals, but how different the story might have been if one asteroid had been larger, or one collision had struck elsewhere. Would life have recovered, or would the spark have been extinguished forever? These are questions we cannot answer. All we can say is that Earth endured, and so did life, leaving us the fragments of their story carved into stone. One of the subtler but equally important consequences of the Orosirian was the way impacts and mountain building worked together to expose the deep crust. The Vredefort impact, for example, not only excavated an immense crater, but also revealed rocks that had formed more than 3 billion years earlier. rocks that today geologists can study as some of the oldest preserved layers of the continental crust. In this sense, the violence of the impact turned Earth inside out, bringing ancient materials from deep within the crust to the surface. These windows into the past are why scientists travel to places like Vredefort today, to see not only the scars of a collision, but also the hidden foundations of the continents themselves. The mountain belts of the Orosirian carried a similar duality. Orogenies are destructive in the short term, volcanoes, earthquakes, folding of entire landscapes, but creative in the long term. They produced highlands that altered rainfall, created rain shadows, and carved new drainage systems. Sediments eroded from these mountains were deposited into deep basins, where they preserved records of changing oceans and atmospheres. These thick sedimentary successions are among the most valuable archives for reconstructing Earth's Paleo-Proterozoic environment. Without mountain building, we would lack these books of stone in which much of the early story of life and oxygen is written. Volcanism tied to these orogenies also played its role. The collision of continental blocks triggered magmatism that pumped fresh gases into the atmosphere and delivered trace metals to the oceans. Molybdenum, nickel, and copper became more available in seawater, all of them essential cofactors for enzymes that microbes use. This quiet geochemical enrichment may have underpinned new metabolic pathways, giving life tools it had not previously possessed. It is a reminder that the emergence of complex biochemistry was not purely biological. It was also fed by tectonics and volcanism, delivering the right ingredients into circulation. The Orosirian is also the time when we first see convincing evidence of large sedimentary basins filled with red beds, rocks stained by iron oxides. These indicate not only that oxygen had reached the atmosphere, but that it was stable enough in some intervals to rust continental sediments. They mark a world where the great oxidation event was no longer a single pulse, but a sustained, if uneven, transformation. Each layer of red sandstone or siltstone is a page in the history of how air became breathable, even if only for future life that did not yet exist. All of this, the asteroid impacts, the mountain belts, the enrichment of oceans, the staining of sediments, illustrates how interconnected Earth's systems had become by the Orosirian. No event stood alone. Cosmic debris striking the surface influenced crustal geology. Crustal geology influenced nutrient delivery. Nutrients shaped microbial metabolisms. Those metabolisms altered the air, and the air in turn fed back on climate and erosion. The Orosirian was not just an age of impacts and mountains. It was a demonstration that Earth had become a fully integrated system, where the sky, the crust, the oceans, and the biosphere could no longer be disentangled. Can land masses already form a puzzle this early? That is the question of the Stotherian, a period stretching from 1.8 to 1.6 billion years ago, when Earth assembled its first true supercontinent, a landmass we call Columbia. The name is modern, but the idea is ancient. Separate cratons and fragments that had grown throughout the Archean and Paleoproterozoic fused into a coherent whole, a continental giant stitched together by belts of mountains. The existence of Columbia is inferred from rock patterns spread across what are now distant continents. When geologists match these pieces, they see sutures and seams that line up like an immense puzzle, fragments that once touched before being scattered again. To imagine Columbia is to imagine a world where most of Earth's continents were united, a world where the face of the planet was dominated not by isolated cratons, but by a sprawling, continuous landmass. Evidence for Columbia comes from orogenic belts that date to this time, mountain chains where continents collided and welded. In North America, the Trans-Hudson orogeny marks such a suture, tying together large cratons into a stable block. In Siberia, India, and South America, rocks of similar age show matching structures. When traced across continents, these belts suggest that many of Earth's major cratons were once neighbours. It is not a perfect map. Erosion and later tectonics have erased much of the detail, but the broader pattern is persuasive. For perhaps 200 million years, Columbia stood as a supercontinent before eventually fragmenting again. The assembly of Columbia brought stability. Once cratons were joined and the crust thickened, large portions of the continents resisted recycling into the mantle. This stabilisation allowed sediments to accumulate over vast areas, producing continental shelves and interior basins where shallow seas lapped against long coastlines. These new environments supported microbial mats and stromatolites, which flourished in warm, nutrient-rich waters. The abundance of stromatolites in the Stetherian rock record suggests life was thriving in these shallow environments, undisturbed by the dramatic climatic swings of earlier ages. Perhaps the most extraordinary event of the Stetherian, however, occurred not on the surface but within the rocks themselves, the Oklo Natural Nuclear Reactor. In what is now Gabon, West Africa, deposits of uranium formed in such concentrations that around 1.7 billion years ago nuclear fission began spontaneously. Groundwater seeping into the ore moderated reactions, allowing sustained chain reactions to occur intermittently for hundreds of thousands of years. This was nuclear power long before humans discovered it. The Oklo reactors left behind distinct isotopic signatures that geologists study today, a reminder that natural processes can achieve what we often think of as purely technological feats. The fact that such a reactor could operate naturally was only possible in an oxygenated world, since uranium must be soluble and concentrated by water to accumulate. The Oklo phenomenon is thus a direct consequence of the Great Oxidation Event, linking microbial photosynthesis to nuclear fission in the deep crust. Columbia's vast size also influenced global climate and chemistry. Supercontinents reduce the amount of coastline relative to area, which can limit shallow marine habitats. They alter ocean circulation, concentrating heat and nutrients differently than smaller scattered continents. Their presence at certain latitudes affects planetary albedo, reflecting more or less sunlight depending on whether land or ocean dominates the equatorial zone. In Columbia's case, evidence suggests that it stretched across equatorial and tropical latitudes, likely influencing global circulation patterns in ways we cannot fully reconstruct. The tectonic assembly of Columbia also drew down carbon dioxide through mountain building and weathering. As ranges rose and eroded, fresh rock surfaces reacted with atmospheric carbon dioxide, binding it into carbonates and reducing greenhouse warming. Combined with the still dim sun, this may have made Earth cooler and more stable than before. The climate of the Stetherian appears less volatile than that of the Rhaetian, perhaps because the presence of a large supercontinent helped regulate feedbacks between weathering, greenhouse gases, and temperature. The tectonic assembly of Columbia also drew down carbon dioxide through mountain building and weathering. As ranges rose and eroded, fresh rock surfaces reacted with atmospheric carbon dioxide, binding it into carbonates and reducing greenhouse warming. Combined with the still dim sun, this may have made Earth cooler and more stable than before. The climate of the Stetherian appears less volatile than that of the Rhaetian, perhaps because the presence of a large supercontinent helped regulate feedbacks between weathering, greenhouse gases, and temperature. For life, this stability was a double-edged sword. On the one hand, stromatolites thrived in calm, shallow seas, leaving abundant fossils in the rock record. On the other hand, diversity appears to have plateaued. Some scientists call this the boring billion, a long stretch of Earth history where little seemed to change in terms of biological complexity. The Stetherian marks the beginning of that stretch. Microbes were abundant, ecosystems stable, oxygen present but not yet at modern levels. It was a world of stasis, but also of quiet preparation for revolutions to come. Another overlooked aspect of Columbia's formation is the way its sheer size influenced the deep mantle beneath it. When such vast tracts of crust sit immobile, they act like insulating blankets, trapping heat in the mantle below. This may have led to the build-up of thermal anomalies, regions of hotter mantle that eventually forced their way upward as large igneous provinces. Evidence of such magmatic outpourings appears in dike swarms and basalt flows dating from this time, stretching across what are now different continents, but once would have been stitched together in Columbia. These intrusions not only reshaped the crust, but also released volcanic gases into the atmosphere, adding further complexity to climate regulation. The joining of continents also reorganized weathering regimes. In earlier times, when land masses were scattered, rainfall and river systems distributed sediments broadly across narrow continental shelves. Columbia, however, concentrated its drainage into massive systems that emptied into fewer but much larger basins. Sediments piled thickly in these basins, burying organic matter and sequestering carbon in ways that altered the long-term carbon cycle. These deposits provide some of the clearest stratigraphic records we have of Paleo-Proterozoic oceans, preserving isotopic signals of how carbon, sulfur, and oxygen cycled through the biosphere. One fascinating development tied to this new continental scale was the appearance of some of the earliest known eukaryotic microfossils. While bacteria still dominated, hints of larger, more complex cells appear in rocks around 1.6 to 1.8 billion years ago. They are sparse and controversial, often little more than microscopic vesicles, with features that suggest internal compartmentalization. If these interpretations are correct, then the stability provided by Columbia's supercontinental configuration may have given eukaryotes their earliest chance to expand. They did not yet dominate, but they were present, quietly testing evolutionary strategies that would eventually redefine the biosphere. The Stitherian also left us with unusual mineral deposits, particularly of iron and manganese, which formed in large basins along Columbia's margins. These were tied to oscillations in ocean chemistry as oxygen levels fluctuated. The scale of these deposits, stretching across entire provinces, reflects the size of the new supercontinent. Mining of these ores today continues to provide vital resources for human industry, yet their origin lies in the interplay between ancient microbes and continental assembly nearly 2 billion years ago. Finally, Columbia's existence forces us to reconsider the tempo of geological change. Supercontinents are not permanent, but their assembly and breakup set the stage for global cycles of nutrients, oxygen, and climate. The Stitherian shows us the first clear instance of this rhythm. Cratons collide, mountains rise, seas shift, biogeochemical cycles adjust, and life responds. It is a cycle that will repeat with Rodinia, Gondwana, and Pangaea, but here, in Columbia, the pattern was established for the first time. Why did it take so long for a cell to invent a nucleus? That is the question of the Columbian, spanning 1.6 to 1.4 billion years ago, when the great leap from prokaryotic life to eukaryotic life finally appeared in force. For nearly 2 billion years, Earth was dominated by bacteria and archaea, organisms that thrived with streamlined simplicity. They lived without nuclei, without mitochondria, without any of the internal architecture that defines our own cells. They were efficient, resilient, and everywhere, but they remained relatively small and limited in complexity. Then, at some point in this window, a transformation occurred. A new kind of cell appeared, one with a nucleus to hold its genetic material and compartments to separate functions. This was the birth of the eukaryotes, and it changed the trajectory of life forever. The emergence of eukaryotes was not inevitable. It required a remarkable event, or perhaps a series of them known as endosymbiosis. In its simplest description, one cell engulfed another, and instead of digesting it, the two formed a partnership. The engulfed cell became an organelle, an internal component that specialized in a task. The most famous example is the origin of mitochondria, the powerhouses of eukaryotic cells, which evolved from free-living bacteria. Mitochondria retain their own DNA, a genetic fossil that still testifies to their independent ancestry. A similar story lies behind chloroplasts, the organelles of photosynthesis in plants and algae, though they evolved somewhat later. Endosymbiosis was not just cooperation. It was a merger that permanently fused lineages. The nucleus itself was another leap. In prokaryotes, DNA floats freely in the cytoplasm, a tangle of genetic instructions continually exposed to the chemical reactions of the cell. In eukaryotes, the DNA is enclosed in a membrane, protected and organized. This allowed for more sophisticated regulation of genes, more control over when and how proteins were produced, and greater potential for complexity. With a nucleus came the capacity to handle larger genomes, which in turn allowed more elaborate cellular machinery. The invention of the nucleus was less dramatic than the invention of mitochondria, but in evolutionary terms it was just as transformative. Why did it take so long for this to happen? Life had existed for over 2 billion years before the first eukaryotes. Perhaps the conditions were finally right. Oxygen levels had stabilized enough to support aerobic metabolism, which gave mitochondria their advantage. Nutrients supplied by continental weathering may have allowed cells to grow larger, experimenting with internal complexity. Perhaps the right symbiotic partnerships were simply rare. dependent on chance encounters that finally aligned. We cannot know for certain. The fossil record of microbes is faint, and molecular clocks offer only broad estimates. What we do know is that by the Calamine, eukaryotes had arrived, and the biosphere would never be the same. Fossil evidence supports this timing. Microfossils from the Calamine show cells larger than typical bacteria, with structures that resemble walls, spines, and internal compartments. One of the earliest candidates is Grippinia spiralis, a ribbon-shaped fossil found in rocks as old as 1.6 billion years. Though its interpretation is debated, many consider it an early eukaryote, perhaps even multicellular. Other fossils show spheroidal cells with ornamented walls preserved in sediments across multiple cratons. They are not numerous, but they suggest that by this time eukaryotes were diversifying into forms more complex than anything that had come before. The Calamine also coincides with geological stability. The supercontinent Columbia remained intact, offering broad, shallow seas where sediments accumulated and microbial mats flourished. These stable environments may have been crucial. For complex cells to evolve, they needed both ecological space and chemical resources. Quiet oceans, rich in nutrients and bathed in moderate levels of oxygen, provided a platform for experimentation. The very stability that some scientists call the boring billion may have been the cradle of complexity. In a world without constant upheaval, cells could refine new strategies slowly, over tens of millions of years. At the biochemical level, eukaryotes were transformative. With mitochondria, they could generate energy far more efficiently than prokaryotes. With a nucleus, they could handle more DNA, supporting larger genomes and more diverse proteins. With internal membranes, they could separate processes, reducing interference and allowing specialization. Each of these changes multiplied possibilities. Eukaryotes were still single-celled, but they had laid the groundwork for multicellularity, for differentiation, and eventually for the evolution of plants, animals, and fungi. It is easy to overlook how radical this was. For billions of years, life had been constrained to small, simple forms. Suddenly, cells could grow larger, build structures, and interact in new ways. The invention of the nucleus and the adoption of symbiosis were like upgrading from stone tools to an industrial workshop. They did not guarantee complexity, but they made it possible. By the end of the Calamine, around 1.4 billion years ago, eukaryotes were present in multiple forms across the globe. They were still rare compared to bacteria, and they did not yet dominate ecosystems. But their presence marked a new chapter. The puzzle of life had gained new pieces that could be combined in ways prokaryotes could never achieve. The haunting question is why this leap occurred only once, or at least why only one lineage of eukaryotes survived. If endosymbiosis was possible, why did it not happen repeatedly? Was it such an improbable event that it nearly failed to occur at all? Or were there other experiments that left no trace, lost to extinction? We may never know. What we can say is that when the nucleus arrived, life crossed a threshold it would never retreat from. One of the subtler consequences of the arrival of eukaryotes was ecological reshaping. Until now, bacterial mats and stromatolites had been the dominant architects of shallow seas. Their layered growth produced reefs of stone, steady but largely uniform. The introduction of eukaryotes began to disturb that order. Larger cells with more flexible metabolisms interacted differently with their surroundings. They grazed, filtered, and shaded. They may even have begun to prey on smaller bacteria, initiating an ecological arms race that altered microbial landscapes. Stromatolite abundance, which had peaked earlier, began to decline gradually through this billion-year interval. It was not disappearance, but a slow reduction, as new players entered the stage and disrupted the quiet monopoly of prokaryotic mats. The internal complexity of eukaryotic cells also created new possibilities for cooperation. Whereas bacteria often lived in dense colonies but remained individually similar, eukaryotes could begin experimenting with differentiation. Some evidence suggests that simple colonial eukaryotes, perhaps with cells performing slightly different roles, already existed in this window. If so, this would have been the faint beginning of multicellularity, an idea that would later explode into the great diversifications of the Neo-Proterozoic. The Calamine does not yet show large organisms, but it may contain the first whispers of them. Another important shift was in the cycling of trace metals. With oxygen present in the oceans, albeit at low concentrations, elements like molybdenum and copper became more soluble. These are essential cofactors for enzymes involved in respiration and nitrogen fixation. Eukaryotes, with their more energy-demanding internal structures, may have been uniquely positioned to exploit these new chemical resources. The geochemical backdrop of the Columbian was not simply passive scenery. It was the stage that allowed a new style of life to survive and expand. This was also a time when Earth's surface environment was unusually calm compared to earlier ages. After the climatic chaos of the Paleoproterozoic, and before the glaciations of the Neoproterozoic, the Mesoproterozoic is sometimes portrayed as uneventful. But for emerging eukaryotes, this stability may have been vital. Constant environmental swings can drive adaptation, but they can also extinguish fragile novelties. The relative quiet of the Columbian gave space for eukaryotic lineages to refine their internal machinery without being snuffed out by sudden planetary upheaval. It was evolution at a patient pace. Looking back, it is tempting to see inevitability here, as if the nucleus and mitochondria had to appear given enough time. Yet when we compare Earth with other worlds in our solar system, none show evidence for such a leap. Simplicity is easy, complexity is rare. That it happened here, once, during the Columbian, is one of the great improbabilities of natural history. The haunting question remains: if this innovation had never occurred, would Earth have remained forever a microbial planet, its continents weathered by mats, its oceans stirred by bacteria, its skies unchanged by higher life? Or was the invention of the nucleus unavoidable, the outcome of chemistry playing long enough on a stable world? All we can do is acknowledge the limits of our evidence and remain humble before the mystery. Why did Earth's inner core form so late? To understand the ectasion, between 1.4 and 1.2 billion years ago, we need to look not at the surface of the planet, but into its deep metallic heart. Earth had existed for more than 3 billion years before the inner core began to crystallize. For much of that earlier history, the core had been entirely liquid, a swirling ocean of molten iron and nickel surrounding the very centre of the planet. Only in the Mesoproterozoic do we see signs that the very innermost region of this metallic sea began to solidify, creating the inner core we know today. It is a reminder that Earth is still cooling from its fiery birth, and that the story of our planet is not only written in rocks and life, but also in the slow freezing of metal far below our feet. The inner core is about 1,200 kilometers in radius, a solid ball of iron alloy that grows slowly as the planet radiates heat into space. Around it lies the outer core, a liquid layer more than 2,000 kilometers thick. Convection in this liquid iron produces Earth's magnetic field, a shield that deflects solar wind and preserves our atmosphere. Without this magnetic field, the surface of the planet would be far more vulnerable to radiation and atmospheric loss, as we see on Mars today. The timing of the inner core's birth matters because the crystallization process releases heat and light elements, fueling convection and strengthening the magnetic field. The ectasion may mark the beginning of this process, when the solid core first nucleated at the centre of the Earth. Why did it take so long? The answer lies in the balance of pressure, temperature, and composition. The core formed early, when heavy elements sank during planetary differentiation, but the centre remained hot enough to stay liquid. Only after billions of years of cooling did temperatures at the very centre drop below the freezing point of iron under immense pressure. The ectasion, therefore, represents a threshold. The planet had cooled enough to allow solid iron crystals to begin growing in the deep interior. This crystallization continues today, with the inner core expanding by millimeters each year. Evidence for when the inner core began to form comes not from direct observation, we cannot sample it, but from the magnetic record preserved in ancient rocks. Paleomagnetic studies of ectasion and later rocks suggest that the strength and stability of Earth's magnetic field increased around this time. Before the inner core, the dynamo in the liquid outer core may have been weaker and more chaotic. With the release of latent heat and light elements from crystallization, convection intensified, producing a more robust and long-lived magnetic shield. This strengthened field may have had profound consequences for the surface, providing more reliable protection against solar radiation and stabilizing atmospheric escape. At the same time, life at the surface continued its quiet expansion. Eukaryotes were diversifying slowly, experimenting with new forms, but ecosystems remained dominated by microbial mats. To them, the deep processes of the core were invisible. Yet indirectly, the improved magnetic field may have contributed to stability that allowed life to persist and diversify. A stronger magnetosphere reduced the erosion of the upper atmosphere by solar wind, helping preserve the balance of gases on which biology depended. It was an unseen protection, born from the silent crystallization of iron thousands of kilometers below. The continents of the Ectasian were still joined as Columbia, the great supercontinent that had assembled in the Stetherian. Vast shallow seas lined its margins, while its interior grew arid. Sediments deposited in these seas preserved stromatolites and microfossils, including some of the earliest ornamented eukaryotic cells. These fossils suggest that the slow evolutionary experiment of eukaryotes was continuing. Life had not yet broken into multicellular radiations, but it was accumulating tools, waiting for its chance. The stable shield of Columbia above and the stabilizing shield of the magnetic field below gave the biosphere time and protection to refine its strategies. The Ectasian is sometimes called unremarkable, part of the so-called boring billion, a long stretch of Earth history with few apparent innovations. Yet in the deep Earth, a quiet revolution was underway. The birth of the inner core was not visible at the surface, but it reshaped the geodynamo and set the stage for billions of years of magnetic protection. It was a change that ensured Earth's atmosphere would endure, making possible the later explosions of complexity and life. If the inner core had not formed when it did, or if the magnetic field had collapsed, Earth's history might have ended as a frozen, desiccated world long before animals or plants arose. By the end of the Ectasian, around 1.2 billion years ago, the inner core was still small, but growing. The magnetic field was stronger and more stable than before. The continents were weathering, the seas still hosted microbial mats, and eukaryotes lingered in the background, slowly expanding. It was not a time of spectacle, but of foundations, both literal and figurative. The haunting question is whether we should think of this age as quiet or monumental. To those who look only at the surface, it was uneventful. But to those who consider the heart of the planet, it was the beginning of a transformation that would shield Earth for the rest of its history. Another way to appreciate the significance of the Ectasian is through the minerals that began to appear in the rock record at this time. Earth's mineral diversity expanded in step with the oxygenation of the oceans and atmosphere, and the strengthening of the magnetic field meant that surface conditions were becoming more stable for weathering and deposition. Minerals such as magnetite and hematite recorded not only redox chemistry at the surface, but also the influence of a more persistent geomagnetic shield. In this sense, the rocks of the Ectasian capture two stories at once: the gradual chemical shift of the biosphere and the deep dynamo flickering to new life far below. Sedimentary basins that formed along the margins of Columbia also preserved another innovation of this time: evidence of complex microbial communities capable of forming extensive biofilms. These were not yet multicellular organisms in the modern sense, but they hint at social behaviours among microbes, where colonies developed coordinated structures rather than acting as isolated individuals. Fossils of filamentous and branching forms suggest organisms experimenting with new geometries, adapting to different microenvironments, and perhaps even specialising within colonies. While subtle, these adaptations foreshadowed the cooperative strategies that multicellular organisms would one day exploit. At the planetary scale, the Ectasian also reminds us that the Earth system is layered. The deep interior, the crust, the atmosphere, and the biosphere all evolve at different paces, sometimes in synchrony, sometimes independently. During this time, the surface world looked static, but the interior was crossing an irreversible threshold. The slow freezing of iron at the centre of the planet is still ongoing today, providing the convective power that sustains the magnetic field. The idea that our atmosphere and oceans, and the very survival of life, depend on processes happening thousands of kilometres below our feet is a humbling reminder of how interconnected the system is. It is also worth noting that the Ectasian marks a midpoint in Earth's timeline. More than 3 billion years had already passed, and yet more than 2 billion years remained before the present. Life had taken hold, but remained largely invisible, its complexity just beginning to emerge. Geology had stabilised into a rhythm of supercontinents, but mountains, oceans and climates still shifted. The inner core's nucleation represents a kind of hinge, a geophysical event that ensured the next half of Earth's story could unfold under the protection of a long-lived magnetic field. Without it, later chapters, the rise of multicellular life, the colonisation of land, even our own existence, might never have been written. Seen this way, the Ectasian is not boring at all. It was the quiet moment when Earth secured its long-term habitability, the slow crystallization of a hidden shield. We measure this event in isotopes and magnetic signatures, but what it meant for the biosphere was stability, continuity, and the chance for evolution to keep experimenting. The haunting thought is how easily it could have been otherwise. If the core had cooled more slowly, if convection had failed, Earth might have followed the fate of Mars, a planet with oceans lost, atmosphere stripped, and life's story cut short. Instead, the inner heart solidified, and the stage remained open for the drama still to come. Was sex just another microbial experiment? To answer that, we step into the Stenian, a period stretching from 1.2 to 1.0 billion years ago. For most of Earth's story so far, life had survived by dividing itself in the simplest way, a single cell splitting into two. This asexual reproduction was efficient and reliable, a method that required no partners and no waiting. But in the Stenian we find evidence of something radically new, something that introduced variation, recombination, and complexity into the very heart of evolution. This is the time of Bangiomorpha pubescens, the earliest known eukaryote to show clear evidence of sexual reproduction. It was not a towering tree or a complex animal. It was a red alga, microscopic and filamentous, preserved in fossilized mats from Canada's Arctic. Yet, in its delicate branching filaments lies one of the most transformative steps in the history of life. The fossil record of the Stenian is sparse, but Bangiomorpha is unusually well preserved in the Shaler supergroup on Baffin Island. These fossils, dated to about 1.04 billion years ago, show structures consistent with differentiated cells in branching filaments, as well as evidence for spore formation. Most importantly, they exhibit patterns that suggest both asexual and sexual reproduction. In some specimens, cells appear to have divided clonally, producing identical offspring as prokaryotes had done for billions of years. In others, however, the structures hint at gametes, specialized cells that fuse to create new individuals with recombined genetic material. If this interpretation is correct, then by the Stenian, life had invented sex. Why does this matter? Asexual reproduction creates clones. It is efficient, but it limits variation. Genetic mutations accumulate, but slowly, and harmful ones can be difficult to purge. Sexual reproduction, in contrast, reshuffles the genetic deck each generation. It allows organisms to combine traits, to hide deleterious mutations, and to generate new variations for natural selection to act upon. In evolutionary terms, sex is both messy and brilliant. It sacrifices the speed of clonal division for the long-term advantage of adaptability. The fact that it appeared so early in the history of eukaryotes suggests that it conferred benefits large enough to outweigh its costs. Bangiomorpha was also significant because it shows the first clear evidence of multicellularity with differentiation. The filaments were not just strings of identical cells. Some cells specialized for reproduction, others for structure. This division of labour was a small step, but an essential one. Multicellularity requires cooperation, and cooperation often begins with reproductive specialization. To see it happening in red algae more than 1 billion years ago suggests that multicellular strategies were already being tested long before animals or plants appeared. The environment of the Stenian was stable compared to earlier ages. The supercontinent Columbia still dominated, though it was beginning to fragment. Shallow seas spread across continental margins, bathed in sunlight and nutrients from weathering land masses. Oxygen levels were higher than in the Archean, though still lower than today, creating layered oceans where microbial mats, cyanobacteria, and eukaryotic algae all shared space. In such conditions, competition would have been intense. The ability to reproduce sexually, generating new genetic combinations, may have offered an edge in crowded ecosystems. Even at microscopic scales, the evolutionary race favoured those who could innovate. The appearance of sex also implies something profound about the tempo of evolution. For billions of years, life remained simple, and then within a relatively narrow window of geological time, it acquired nuclei, mitochondria, and sexual reproduction. Each step built on the last, compounding the potential for complexity. In hindsight, it seems like a rapid acceleration, though in human terms it still spanned hundreds of millions of years. Yet compared to the 3 billion years of microbial stasis before, the Mesoproterozoic represents a burst of experimentation that set the stage for the Neoproterozoic and the eventual rise of animals. We must be cautious, however. Not all scientists agree on the interpretation of Bangiomorpha. Fossils are fragmentary, and the evidence for sex is indirect. Some argue the structures could be explained by asexual processes or by convergent forms unrelated to modern red algae. The debate continues, and humility is necessary. What we can say is that by around 1 billion years ago, eukaryotes were branching into new strategies, and sexual reproduction was either already established or very near to its origin. The transition was underway. By the end of the Stenian, around 1.0 billion years ago, Earth was populated by a mixture of microbial mats, cyanobacteria, and eukaryotic algae, experimenting with new ways to reproduce and organize. Mountains rose as Columbia gave way to Rodinia, basins filled with sediments, and shallow seas nurtured the slow diversification of complex cells. The haunting question is why sex, once it appeared, became nearly universal among eukaryotes. Was it simply too advantageous to ignore, or did lineages without sex fade quietly into extinction, leaving no descendants to tell their tale? Whatever the answer, the Stenian left us with the first fossil evidence of an act that reshaped evolution, the fusion of two cells to create something new. Another way to grasp the importance of the Stenian is to look at what sexual reproduction did to the pace of genetic change. Asexual lineages, though successful, are bound by what biologists sometimes call Muller's ratchet, the slow, irreversible accumulation of harmful mutations. Without recombination, once a deleterious mutation is fixed in a lineage, it cannot easily be purged. Sexual reproduction, by contrast, allows harmful variants to be shuffled, masked, or eliminated across generations. This meant that for the first time in Earth's history, life had a mechanism not only for creating novelty, but also for cleaning up its own mistakes. In evolutionary terms, it was a strategy that promised longevity. The fossilized traces of Bangiomorpha also invite us to think about what it means for organisms to cooperate. Multicellularity demands sacrifice. Cells that specialize in reproduction depend on others that provide structure or support. In bacteria, where each cell is a self-contained individual, such cooperation is rare. But in red algae, we see the first faint hints of cellular altruism. Some cells gave up their chance to reproduce in order to support the colony as a whole. It is a dynamic that would later become central to the rise of complex life. Individuality dissolving into collective identity. From a planetary perspective, the timing of sex and early multicellularity is intriguing. The Stenian sits just before the assembly of the supercontinent Rodinia, an event that would reshape ocean currents, nutrient cycles, and climate. The oceans of this period were already becoming layered, with oxygenated surface waters and deeper anoxic zones. This stratification created niches where different strategies could thrive. For eukaryotic algae experimenting with sex, the ability to generate variation may have been a way of hedging bets in an environment where conditions could shift subtly but significantly over millennia. It is tempting to think of sex as inevitable, but nothing in biology is certain. Some prokaryotes developed limited forms of gene transfer, such as plasmids or viral exchange, but they never evolved full sexual cycles. In that sense, the rise of sex among eukaryotes was not just a continuation of microbial strategies, but a departure into something qualitatively new. The fact that nearly all eukaryotic lineages today retain some form of sexual reproduction, even those that reproduce asexually most of the time, suggests that once established, it became deeply entrenched. It may have been costly, but abandoning it completely would have meant surrendering long-term adaptability. The Stenian does not offer us dramatic animals or forests, but it gives us something subtler, a new mode of inheritance. It was a turning point where evolution armed itself with the ability to reinvent life generation after generation, rather than relying on chance mutations alone. The haunting thought is that if Bangiomorpha or its kin had not made this leap, evolution might have stalled at microbial mats and simple colonies. Instead, sex became the fuel for future complexity, a quiet revolution carried out in the shallow seas of a billion-year-old world. What happens when life eats life for the first time? To ask that question is to step into the Tonian, the long stretch of time from 1 billion to about 720 million years ago. For billions of years before this age, life had been busy enough, photosynthesizing, fermenting, oxidizing minerals, building stromatolites and spreading into mats. But in all that time, organisms had rarely, if ever, directly attacked and consumed one another. Energy was harvested from sunlight or from chemical reactions with the Earth itself, but not by engulfing another living being. In the Tonian, something changed. Eukaryotic cells, already more complex than bacteria, began to experiment with predation. They learned to engulf and digest other cells, creating the first ecosystems where life fed on life. It was the dawn of a new ecological dynamic, one that still shapes our world today. The evidence for this shift comes from microfossils found in sedimentary rocks of Tonian age. Among them are forms called acritarchs, microscopic organic walled vesicles with elaborate ornamentation. Some have spines, ridges, or thickened walls, features that many paleobiologists interpret as defences against being eaten. Their sudden appearance in the Tonian fossil record suggests that predation had begun. If no one were trying to eat them, why would microorganisms invest the energy to build protective armour? Just as thorns make sense only in a world with herbivores, spiny microfossils make sense only in a world where predators were now hunting prey. These predators were not animals. They were protozoans, single-celled eukaryotes that had mastered phagocytosis, the ability to engulf other cells into a pocket of their own cytoplasm and digest them. To a bacterium, such predators would have been terrifying, a sudden new threat that could not be avoided by simply existing in a mat. The evolutionary arms race began, prey cells developing walls, armour, or toxins, predators evolving sharper ingestion mechanisms or ways to bypass defences. For the first time, survival was not just about finding energy, but about escaping being consumed. This innovation rippled through ecosystems. Predation changes everything. It alters population sizes, shapes food webs, and drives diversification. In the Tonian, it likely contributed to the increase in morphological complexity we see in microfossils. Organisms that had once been simple spheres began to branch, elongate, or decorate their surfaces. Each adaptation was a response to selective pressures imposed by predators. The ocean, once a relatively static soup of microbial mats and plankton, became a dynamic battlefield of invisible wars. Geochemically, the Tonian was also significant. Oxygen levels were gradually rising, though not yet at modern levels. This oxygen provided the metabolic support needed for predation. Engulfing and digesting another cell is energetically costly. Without sufficient oxygen to fuel mitochondria, such behaviour would be inefficient. The slow but steady oxygenation of surface oceans may have provided the threshold that allowed protozoan predators to thrive. Once they did, they restructured ecosystems in ways that made later evolutionary explosions possible. Continents, too, were on the move. The Tonian is the age when the supercontinent Rodinia assembled, bringing together nearly all of Earth's land masses into a vast configuration that stretched across equatorial regions. Rodinia's formation altered ocean currents, weathering rates, and nutrient cycles. Large rivers carried phosphorus, nitrogen, and trace metals into shallow seas, fertilizing ecosystems and supporting microbial blooms. More nutrients meant more opportunities for eukaryotes to grow large, diversify, and test new ecological strategies like predation. The assembly of Rodinia and the rise of protozoan predators are not unrelated. They were part of a planetary system that was beginning to hum with new levels of interaction. Another key development of the Tonian was the appearance of testate amoebae, microorganisms that constructed shells around themselves. Fossils of these tiny armoured amoebae have been discovered in Tonian deposits, pushing back the record of such complex behaviours. The construction of a shell requires both genetic instructions and environmental resources, meaning that by this time, eukaryotes had evolved not just predatory habits, but also architectural ones. Life was becoming more inventive. The Tonian also saw the beginning of the diversification of the green algae, ancestors of plants. Fossil evidence indicates that they were already experimenting with multicellular structures, branching filaments, and differentiated cells. These algae would eventually give rise to the land plants that transformed Earth's surface, but here in the Tonian, they remained small players in the oceans. Still, in combination with predatory protists, they added complexity to food webs that were no longer just microbial mats passively absorbing sunlight. To imagine the Tonian Ocean is to imagine a world still dominated by microorganisms, but no longer in a static equilibrium. It was now a world of interactions, of chase and escape, of strategies and counter-strategies. The simplicity of the early biosphere was gone. In its place was a living system where the fates of organisms depended on the actions of others, not just on the chemistry of the environment. By the end of the Tonian, around 720 million years ago, life had been irrevocably changed. Predation had entered the evolutionary equation, and with it, the arms race that would eventually lead to shells, skeletons, mobility, and nervous systems. The haunting question is whether this step was inevitable, or whether Earth could have remained a world of passive mats and photoautotrophs. Was predation the necessary spark for the later explosion of animal life, or was it simply one of many possible paths? We cannot know for certain. But the Tonian gives us our first clear evidence that life was no longer content simply to endure. It was now consuming, competing, and inventing at a new scale. One way to appreciate the scale of change in the Tonian is to think about energy. For billions of years, microbial life had lived on the margins of what chemistry allowed. Sunlight drove photosynthesis. Simple chemical gradients across membranes powered respiration. Nutrients were recycled slowly in mats. But predation opened a new, concentrated source of energy. A living cell was far richer in carbon, nitrogen, and phosphorus than any mineral or dissolved molecule drifting in seawater. To consume another cell was to tap into a dense package of nutrients, a shortcut to growth. This new economy changed the logic of survival. Organisms were no longer just competing for sunlight or dissolved ions. They were competing to avoid being eaten or to become better hunters. The fossil record of the Tonian, though fragmentary, captures this transition in suggestive ways. Acritarchs with spikes and thick walls, testate amoebae with protective shells, and filamentous algae with branching structures all point toward an ecosystem under pressure. These features were not merely decorative. They were investments of energy into protection, signalling that the threat of predation was real enough to justify costly defences. Just as armour and weaponry would later define animal evolution, here we see their microbial equivalents emerging in miniature. The assembly of Rodinia also played a role in amplifying these dynamics. Vast continental margins created wide shelves where sunlight penetrated shallow waters, producing fertile zones for algae and cyanobacteria. These blooms provided the biomass that predators needed to thrive. The feedback loop was clear. More nutrients led to more primary production, which supported larger populations, which in turn sustained more predators. For the first time, the oceans may have seen microbial boom and bust cycles where predators temporarily overgrazed prey populations, only to decline themselves until the balance returned. This oscillation, familiar in modern ecosystems, likely had its roots in the Tonian. There is also evidence that the diversification of predators encouraged greater ecological partitioning. Instead of vast mats covering seafloors uniformly, microorganisms began occupying distinct niches, some clinging to mineral grains, others floating in the plankton, still others burrowing into sediments. This spatial complexity created new opportunities for interaction, increasing the richness of early ecosystems. The simple, layered microbial worlds of the Archean and Paleoproterozoic gave way to more textured communities, where behaviour mattered as much as chemistry. Seen in this light, the Tonian was not just a quiet prelude to the more dramatic glaciations of the Cryogenian. It was a crucial turning point where the ecological rules of the biosphere changed. The invention of predation introduced a new dimension to evolution, one that would eventually lead to mobility, sensory systems, and the cascade of innovations we recognise in animals. Yet it began invisibly, in microscopic encounters in the Tonian seas, where a single-celled predator engulfed another cell, and the world was never the same. How do you survive when the planet is encased in ice? That is the question of the Cryogenian, a stretch of time from about 720 to 635 million years ago, when Earth endured some of the most extreme glaciations in its history. The very name of the period means cold-born, and with good reason. Geological evidence from nearly every continent shows deposits of glacial origin sitting at tropical paleolatitudes. Dropstones, large chunks of rock carried by icebergs and dropped into fine marine sediments, are found in places that were near the equator at the time. Carbon isotope anomalies reveal disruptions in the carbon cycle, consistent with massive ice coverage. The picture that emerges is of a world that may have been locked in ice from pole to pole, the so-called Snowball Earth. The causes of these glaciations are still debated, but one leading hypothesis ties them to the rise of photosynthetic eukaryotes and the gradual drawdown of atmospheric carbon dioxide. As algae spread in the oceans, they consumed carbon dioxide, sequestering it in organic matter that was buried in sediments. Less carbon dioxide meant a weaker greenhouse effect, and once cooling began, ice expanded rapidly. Because ice reflects sunlight far more efficiently than rock or water, it spread reinforced cooling in a feedback loop. With continents clustered near the equator in the configuration of the supercontinent Rodinia and its later fragments, glaciers could advance across low latitudes, where the sun's energy is strongest. Once ice reached those zones, the planet may have tipped into a global freeze. If Earth really was encased in ice, the survival of life seems miraculous. Photosynthesis requires sunlight, but thick ice would have blocked it. Yet life persisted, and later flourished. How? Several refugees are proposed. Thin equatorial regions of ice may have allowed light to penetrate shallow seas, supporting photosynthetic communities beneath. Hydrothermal vents and volcanic hot springs could have sustained chemosynthetic organisms independent of sunlight. Brine channels within sea ice, where salt water remained liquid, may have harboured microbial ecosystems. Even beneath kilometres of ice, life could cling to volcanic oases or deep-sea vents. The Cryogenian shows us the resilience of biology in the face of planetary catastrophe. The duration of these glaciations was extraordinary. Some estimates suggest that individual snowball events lasted for tens of millions of years. The Sturtian glaciation, beginning around 720 million years ago, may have persisted for 50 million years. Later, the Marinoan glaciation, ending about 635 million years ago, may have locked the world in ice for another 15 million. These spans are immense, long enough to reshape both the surface of the planet and the course of evolution. When Earth finally thawed, the biosphere emerged into a transformed world. What ended the snowballs? Volcanism provides a likely answer. Even under ice, volcanic outgassing continued, releasing carbon dioxide into the atmosphere. With weathering slowed by ice cover, carbon dioxide accumulated. Eventually, greenhouse warming overcame the reflective cooling of the ice, and the planet thawed catastrophically. The evidence lies in cap carbonates, thick layers of carbonate rock deposited directly on top of glacial sediments. These carbonates suggest a sudden, massive influx of carbon dioxide, ocean acidification, and chemical overshoot after the ice melted. The release from snowball conditions was not gentle. It was a swing from one extreme to another, an Earth lurching between frozen desolation and greenhouse heat. The evolutionary consequences of the Cryogenian are profound. Extreme stress can drive innovation, and many scientists see these glaciations as crucibles for complexity. Populations isolated in refuge may have undergone genetic bottlenecks, accelerating divergence. Predation, already established in the Tonian, would have intensified pressures for defence and innovation in constrained ecosystems. When the ice receded, eukaryotes expanded into newly opened habitats, diversifying rapidly. It is in the wake of the Cryogenian that we see the rise of the first large multicellular organisms of the Ediacaran. We must be careful, though, not to romanticize the snowballs as mere preludes to complexity. They were disasters. Whole ecosystems must have collapsed, countless lineages vanished, and survival was a matter of chance as much as adaptation. The haunting thought is how close life may have come to annihilation. Had the ice persisted longer, had volcanic outgassing been weaker, Earth might have remained a frozen planet, its story of complex life cut short. Instead, it thawed, and life emerged not only intact but invigorated, ready to explore new possibilities. By the end of the Cryogenian, the planet had swung from freeze to thaw, glaciers retreating, seas flooding continental margins, and new chemical regimes sweeping through the oceans. It was a world shaken, reset, and full of opportunity. The question lingers, was the Snowball Earth a catastrophe or a gift? Perhaps both. It was a disaster for many lineages, but it carved out the conditions that allowed the rise of the first animals. In the silence of a frozen planet, the seeds of future complexity were waiting. One of the more subtle consequences of global glaciation was the way it reworked Earth's surface chemistry. With continents covered by ice and erosion slowed, the normal recycling of nutrients into the oceans would have been drastically reduced. Phosphorus, iron, and other key elements that normally washed in through rivers would have been trapped beneath glacial sheets. This nutrient famine likely suppressed productivity, further stressing ecosystems already constrained by darkness and cold. Yet, paradoxically, the end of glaciation may have released a flood of nutrients all at once. As glaciers ground across bedrock and then melted, they delivered fresh mineral powders into the oceans. These glacial fertilizers may have fueled explosive algal blooms in the aftermath of the snowballs, creating new ecological opportunities just as eukaryotic life was poised to expand. Geologists studying Cryogenian strata also point to curious banded iron formations that reappear after being absent for more than 1 billion years. These deposits suggest that during snowball episodes, the oceans became largely anoxic once again, with dissolved iron accumulating in the absence of oxygen. When the ice melted, oxygenated waters returned, oxidizing the iron and depositing it as layered formations. This cycle highlights how intimately tied climate, ocean chemistry, and the biosphere were. The snowballs were not just surface spectacles of ice, they were events that reset redox balances across the entire ocean system. Another clue comes from the isotopic record of sulfur and carbon. Both show unusual fluctuations during the Cryogenian, indicating instability in the global carbon cycle and in microbial metabolisms. These chemical swings point to stressed ecosystems where microbial communities struggled under changing conditions. Sulfur isotope anomalies in particular suggest that sulfate-reducing bacteria continue to operate in restricted environments, even beneath kilometers of ice. The persistence of these microbial metabolisms reminds us that life is adaptable, able to find chemical footholds in the narrowest of niches. The landscape itself would have been unrecognizable. Imagine glaciers extending into equatorial seas, mountains scoured to their cores, and oceans capped by ice stretching horizon to horizon. Volcanic islands may have erupted through the ice, offering pockets of warmth and liquid water around their margins. Beneath the frozen surface, hydrothermal systems continued, pumping energy and chemicals into dark waters. For organisms adapted to such extremes, the Cryogenian was not an interruption, but a new normal. The survival of lineages that later gave rise to animals testifies to the ability of life to withstand unimaginable stress. What makes the Cryogenian especially haunting is its duality. On one hand, it was a global catastrophe that could easily have extinguished much of life. On the other, it may have primed Earth for the great diversification that followed. The glaciers carved landscapes, released nutrients, and forced biology into refuges that fostered innovation. When the planet thawed, it was not the same world. The stage was set for the Ediacaran, when life would, for the first time, break the limits of the microscopic. Why did life suddenly get big and strange? That question belongs to the Ediacaran, the slice of time from about 635 to 541 million years ago. It followed the end of the Cryogenian snowball catastrophes, when glaciers finally melted and seas flooded back across the continents. Out of that long freeze emerged something entirely new. For the first time in Earth's history, organisms left fossils visible to the naked eye, not just microscopic traces. These were the Ediacaran biota, a menagerie of shapes so alien that scientists still argue about what they were. Some resembled fronds or discs pressed into sandstone. Others were quilted, leaf-like impressions without clear heads, limbs or mouths. They were large, some over a metre long, yet often lacked features we associate with animals. For decades, researchers wondered whether these were early relatives of jellyfish, sponges, lichens, or even an entirely separate experiment in multicellularity that later vanished. The most striking feature of the Ediacaran world was scale. After billions of years of microbial dominance, life suddenly occupied centimetres and then metres. This expansion may have been fueled by the environmental shifts triggered by the end of Snowball Earth. As glaciers retreated, nutrient-rich meltwater surged into oceans, fueling blooms of algae and other primary producers. Oxygen levels in shallow seas rose, perhaps reaching thresholds that could sustain larger, more active organisms. Bigger bodies require more oxygen to diffuse across tissues, and until the Ediacaran, that had been a limiting factor. The rise of atmospheric and oceanic oxygen may have opened the door for multicellular giants to thrive. Fossil assemblages from places like the Flinders Ranges in Australia, the White Sea in Russia, and Newfoundland in Canada reveal whole communities of Ediacaran organisms. They were not solitary oddities, but ecosystems of strange creatures carpeting the seafloor. Some lay passively on sediment surfaces, absorbing nutrients directly from the water. Others appear to have been anchored to the seabed, waving frond-like bodies into currents. A few show evidence of mobility, leaving trackways that hint at muscles and coordinated movement. These communities were the first to transform seafloors into habitats structured by macroscopic life. The diversity of forms is bewildering. There are discs like Aspidella, fronds like Charniodiscus, quilted forms like Dickinsonia, and bizarre radiating fossils like Tribrachidium with its threefold symmetry. Some of these may represent stem groups of modern animal lineages, while others may have no descendants at all. Molecular clock studies suggest that animals such as cnidarians and bilaterians were already diverging in this period, even if their identities in the fossil record remain elusive. The Ediacaran was therefore both a beginning and a dead end, a time when evolution tested shapes and strategies, some of which endured and others that disappeared without a trace. Gondwana also took shape during this period, bringing together much of the southern continents. Its assembly reshaped climates and ocean circulation, creating long continental shelves bathed in nutrient-rich waters. These shallow seas may have been nurseries for Ediacaran organisms, offering expansive habitats where sunlight, oxygen, and nutrients met. The interplay between geology and biology was once again evident. Continental collisions built mountains, erosion carried nutrients to the sea, and life responded by growing larger and stranger than ever before. The haunting question remains: what exactly were these organisms? Were they true animals at the dawn of animal evolution, or an independent branch of multicellularity that flourished for tens of millions of years before vanishing? With only impressions in rock to guide us, the answer is uncertain. What is clear is that by the Ediacaran, Earth was no longer a microbial world. It was home to the first giants of life, heralding the revolution still to come. One underappreciated aspect of the Ediacaran is how these new organisms altered the sedimentary environment. Before this time, seafloors were dominated by microbial mats, sticky carpets of bacteria that stabilize sediments and left behind layered textures called wrinkle structures. The arrival of large multicellular organisms disrupted this balance. Their weight pressed into the mats, their movements disturbed surfaces, and in some cases they may have grazed upon the mats themselves. This shift is recorded in the rock record as a decline in wrinkle structures and the appearance of more complex bedding features. In other words, the Ediacaran biota were not just new inhabitants of the seafloor, they began to engineer it. There is also growing evidence that some Ediacaran forms may have reproduced in surprisingly advanced ways. Certain fossils appear in dense clusters, hinting at synchronized reproduction, perhaps even through the release of propagules or spores into the water. Others are found in linear arrangements that suggest budding, where a parent organism produced a line of offspring directly attached. If true, this would mean that strategies for both sexual and asexual reproduction were already being tested at this early stage. These reproductive experiments may have helped Ediacaran organisms spread rapidly across continental shelves, colonising new environments in ways microbes alone had never done. Ecological interactions were also beginning to take shape. The discovery of faint trackways near Ediacaran fossils suggests that some organisms could move across the sediment, perhaps searching for food or avoiding competition. Though these traces are simple, they foreshadow the complex behaviours that would dominate in the Cambrian. Predation, however, remains a debated topic. There is little clear evidence that Ediacaran organisms were actively hunted, but some specimens show signs of damage or partial consumption. Whether this was true predation or simply decay is unclear. Still, the very possibility that these giants may have been preyed upon suggests that food webs were becoming more intricate than ever before. The eventual decline of the Ediacaran biota is another mystery. Many lineages appear to vanish at the dawn of the Cambrian, replaced by more familiar animals with skeletons and complex body plans. Some paleontologists argue that they were outcompeted by emerging bilaterians, others that changes in ocean chemistry made their quilted bodies unsustainable. It is also possible that their soft bodies simply fossilised poorly compared to shelled animals, leaving an incomplete record. Whatever the cause, their disappearance underscores the experimental nature of this era. Evolution had tested a wide array of possibilities, but only some would persist into the next great radiation of life. Perhaps the most humbling lesson of the Ediacaran is that complexity does not always resemble what comes after. These organisms were not simply primitive versions of modern animals. They were unique solutions to the challenges of their time. Some lineages may have given rise to modern groups, but many were evolutionary cul-de-sacs, flourishing for tens of millions of years before fading away. Their strangeness reminds us that life's path is not straight but tangled, with many branches lost along the way. Why did almost every animal blueprint appear at once? That is the puzzle of the Cambrian, spanning from about 541 to 485 million years ago. For billions of years before this point, life was small, soft-bodied and limited to relatively simple forms. Then, within a geological blink, nearly all of the major body plans that exist today, arthropods, mollusks, echinoderms, chordates, annelids, burst into the fossil record. This is what scientists call the Cambrian explosion, though in truth it was less an instantaneous blast and more a sustained acceleration over tens of millions of years. Still, compared to the deep slowness of previous ages, it was an evolutionary cascade unlike anything that had come before. The record of this explosion is preserved in extraordinary fossil deposits such as the Burgess Shale in Canada and the Chengjiang Formation in China. These Lagerstätten preserve soft-bodied animals in exquisite detail, revealing not only shells and skeletons but also muscles, gills, and sometimes even nervous systems. In these rocks we meet creatures that seem familiar and strange all at once. Trilobites, armoured arthropods with segmented bodies and compound eyes scuttled across sea floors, anomalocaridids, large predators with grasping appendages and circular mouths, patrolled the water column. Early chordates, small fish-like animals with notochords, swam with undulating tails, hinting at our own ancestry. It was a sudden theatre of life, filled with roles that had never existed before. Several factors likely converged to produce this explosion of body plans. One was oxygen. By the Cambrian, atmospheric and oceanic oxygen had reached levels sufficient to support larger, more active animals. Muscles require oxygen to function, and shells require energy to build. Another factor was ecology. The appearance of predators set off evolutionary arms races, driving prey to develop defences such as shells, spines and burrowing behaviours. These defences, in turn, created new opportunities for predators to evolve sharper tools. Diversity fueled diversity in a feedback loop. Geological conditions may have also played a role. The breakup of the supercontinent Rodinia created shallow continental shelves, warm seas, and varied environments where ecosystems could flourish. The invention of skeletons was a watershed moment. Until the Cambrian, most organisms were soft and left little trace. With the evolution of biomineralization, animals began to incorporate calcium carbonate or calcium phosphate into their bodies, building hard shells and exoskeletons. This not only protected them from predators, but also preserved them in the fossil record, creating the apparent suddenness of the Cambrian explosion. Trilobites, brachiopods, and mollusks became common, leaving behind abundant fossils that mark the beginning of modern-style paleontology. Vision also appears to have emerged as a key innovation. Compound eyes in trilobites and anomalocaridids suggest that visual predation was already established. Eyes changed the rules of survival. Suddenly, stealth and speed mattered in new ways. Camouflage, mobility, and defensive morphologies became advantageous, pushing evolution toward ever greater complexity. Some scientists argue that the evolution of vision may have been one of the critical triggers of the Cambrian explosion. The Cambrian seas were dynamic laboratories where new modes of life were tested. Burrowing animals churned sediments, disrupting microbial mats and oxygenating sea floors. Filter feeders extracted plankton from the water column. Grazers scraped algae from surfaces. Predators stalked or ambushed prey. For the first time, ecosystems contained layers of interaction. Primary producers, herbivores, carnivores, and scavengers. Food webs became more intricate, and energy flowed through them in ways that resembled modern ecosystems. It is important to note that the Cambrian explosion did not invent multicellularity or complexity out of nothing. The groundwork had been laid in the Ediacaran and before, with eukaryotes already experimenting with multicellular forms, tissues, and simple animal-like structures. The Cambrian accelerated and consolidated these experiments, locking in the basic body plans that would dominate for the rest of Earth's history. Once established, these plans proved remarkably durable. Despite mass extinctions and environmental upheavals, the fundamental architectures of arthropods, chordates, mollusks, and others persisted. Still, not all Cambrian innovations lasted. Many groups that flourished in this period vanished later, leaving no descendants. The explosion was as much about evolutionary trial and error as it was about success. Creatures like Opabinia, with its 5 eyes and trunk-like proboscis, or Hallucigenia, with spines down its back and legs pointing in odd directions, remind us of the strangeness of early animal life. They are evolutionary experiments, some of which led to thriving lineages and others that ended in extinction. The haunting question is why this particular window of time saw such a concentration of innovation. Was it simply the right combination of oxygen, nutrients, and ecological interactions? Or was there something intrinsic to the genetic and developmental toolkit of animals that unlocked new possibilities? The rise of Hox genes, which regulate body patterning, may have been critical, allowing simple organisms to build complex structures reliably. The Cambrian explosion may thus reflect not only external conditions but also internal genetic innovations. By the end of the Cambrian, around 485 million years ago, the oceans were crowded with trilobites, brachiopods, mollusks, echinoderms, and early vertebrates. The seafloor was busy with burrowers and grazers, the water column with swimmers and predators. Life had expanded into nearly every available niche, creating ecosystems that would feel recognizable in structure even if their inhabitants looked alien. The planet had crossed a threshold. The microbial and enigmatic world of earlier eons had given way to an Earth filled with visible, dynamic, and competitive animals. One of the subtler revolutions of the Cambrian was how animals reshaped the seafloor. For billions of years before, sediments were stabilized by microbial mats, much as they had been in the Ediacaran, but the spread of burrowing creatures, some no larger than a fingernail, began to destabilize these mats. They churned the sediments in search of food or shelter, oxygenating the upper layers and changing the chemistry of the seafloor. This agronomic revolution destroyed the quiet microbial carpets that had once covered continental shelves and created a far more dynamic environment. The rippling effect of such behavior is hard to overstate. By turning over sediments, burrowers altered nutrient recycling, created new habitats, and paved the way for more complex benthic ecosystems. Another theme of the Cambrian is ecological escalation. Once predators evolved, prey could not remain defenseless. Some animals thickened their shells, others burrowed deeper, still others adopted mobility as a shield. Trilobites, for example, developed the ability to roll up into armoured balls, a strategy still used today by pillbugs. Small brachiopods anchored themselves to the seabed with tough stalks, resisting dislodgement. These changes meant that energy was increasingly locked into structural defences, which in turn spurred predators to innovate further. What had begun as a microbial arms race in the Tonian now reached a new level of sophistication. The Cambrian explosion also left us with one of the richest fossil records of any era because of exceptional preservation in certain sites. The Burgess Shale and Xinjiang biotas capture organisms that would normally decay within hours. Fine sediments, rapid burial, and unique geochemical conditions froze soft tissues in stone, allowing us to glimpse creatures that would otherwise be invisible. Without these windows, we might still believe that early animal life was limited to shells and exoskeletons. Instead, we see delicate gills, intestines, and even nerve cords, offering insights into physiology that otherwise would have been lost. These deposits remind us how much of Earth's history depends on the accidents of preservation. Another dimension of the Cambrian was the appearance of truly pelagic lifestyles. For the first time, animals adapted to live permanently in the open water column, not just on or near the seafloor. Jellyfish-like cnidarians floated and drifted, while early arthropods swam with rhythmic strokes of their appendages. This opened new ecological zones, turning the ocean into a three-dimensional stage. Grazers fed on plankton, predators pursued swimmers, and scavengers exploited remains. The oceans became layered ecosystems, with interactions unfolding from the seabed to the surface. Yet the Cambrian was not simply a story of triumph. It also saw its own crises. Fossil evidence points to at least 2 extinction events within the period, where significant fractions of marine diversity were lost. These events remind us that the explosion of forms was not a steady upward climb, but a turbulent process, shaped by both innovation and collapse. Life was experimenting at high speed, but not every experiment survived. By the close of the Cambrian, Earth had become a planet where ecosystems were dense, varied, and competitive. The basic blueprints of animal life were established, sedimentary environments were transformed, and the seas thrummed with energy. What had once been a microbial planet was now a world animated by movement, vision, and predation. The haunting thought is that without this singular acceleration, the later history of animals, including our own, might never have had the foundations on which to build. How did seas full of invertebrates change the world? To find the answer, we enter the Ordovician, spanning from about 485 to 444 million years ago, when Earth's shallow seas became stages for an extraordinary expansion of biodiversity. The Cambrian had given us the blueprints, the first great body plans, but the Ordovician filled those blueprints with life. Trilobites multiplied into countless forms. Brachiopods and bryozoans carpeted the seafloor. Cephalopods grew large, some stretching meters in length, patrolling the seas as apex predators. Coral-like organisms, together with stromatoporoids, began to build the first true reefs. Diversity did not just increase, it soared. By the middle of the Ordovician, marine life had exploded into a richness that rivaled anything seen since, marking one of the great radiations in the history of life. The world itself looked different. Continents such as Gondwana and Laurentia drifted across latitudes, creating broad, shallow seas along their margins. Much of the land lay submerged beneath epicontinental seas, warm and nutrient-rich waters where sunlight reached the seafloor. These shallow platforms provided vast habitats for benthic communities. Sediments preserved fossils in abundance, from trilobite exoskeletons to the delicate lattices of graptolites. The Ordovician fossil record is therefore exceptionally detailed, giving us a window into ecosystems that were both complex and prolific. Reefs played a pivotal role in this transformation. Built by corals, stromatoporoids, and algae, they created three-dimensional habitats where countless species could shelter, feed, and reproduce. Reefs are biodiversity engines, and in the Ordovician they flourished. Their structures redirected currents, concentrated nutrients, and provided hard surfaces in otherwise soft seafloor environments. Fish had not yet risen to dominance, but invertebrates filled every available niche, from filter feeders and grazers to scavengers and predators. It was not only animals that changed the Ordovician world. Evidence suggests that the first land plants, tiny, moss-like organisms, appeared during this period. Their colonization of damp shorelines and riverbanks began a revolution in Earth's geochemical cycles. Even small primitive plants altered patterns of weathering, drawing down carbon dioxide from the atmosphere and feeding nutrients into rivers and seas. Over millions of years, this quiet greening of land would transform soils, reshape climates, and prepare the way for forests. In the Ordovician, however, the story was just beginning, and the plants were modest pioneers, clinging to moist edges rather than sprawling across continents. The Ordovician world was not static. Climate shifts punctuated its history, and tectonics reorganized oceans and continents. Toward the end of the period, a major glaciation struck Gondwana, triggering one of Earth's great mass extinctions. As ice sheets grew, sea levels fell, draining the shallow seas that had nurtured biodiversity. Marine ecosystems collapsed, with trilobites, brachiopods, and many other groups suffering heavy losses. Graptolites, once abundant, nearly vanished. It was the first of the Big Five mass extinctions, a reminder that Earth's prosperity is always fragile. Why did the Ordovician produce such an extraordinary radiation of life, only to end in devastation? One possibility is that rising oxygen levels and nutrient availability supported new evolutionary experiments, while expanding shallow seas provided the space for them to flourish. But when climates shifted and seas receded, the very environments that sustained this explosion became liabilities. Diversity itself was no shield against global environmental change. The extinction eliminated an estimated 85% of marine species, a staggering loss that reshaped ecosystems for millions of years. Yet from this catastrophe, survivors carried forward the evolutionary legacies of the Ordovician. Reefs would recover, trilobites would diversify again, and cephalopods would continue their march toward dominance. Plants on land, unaffected by marine extinction, quietly spread, setting the stage for terrestrial ecosystems. The Ordovician demonstrates both the resilience and vulnerability of life. It shows how rapidly biodiversity can expand in the right conditions, and how quickly it can collapse when those conditions falter. The haunting question that lingers is whether such radiations are inevitable or rare accidents of circumstance. Did life have to expand into the shallow seas with such abundance, or was the Ordovician a unique confluence of geography, chemistry, and chance? What we know is that in these seas, life reached a richness never before seen, only to be pruned harshly by ice, and in that alternation between explosion and collapse, Earth's evolutionary story took on the rhythm that has persisted ever since. Another way to see the Ordovician is through the rise of graptolites, colonial organisms that floated in the water column and left delicate carbon films in black shales. Though often overlooked compared to trilobites or cephalopods, graptolites were extraordinary markers of this age. They lived as colonies suspended from floating structures, each colony composed of many tiny zooids working together. Graptolites spread across the oceans, evolving rapidly, and their fossils are now key tools for dating Ordovician rocks. They represent a new lifestyle, living not on the seafloor, but drifting with currents, forming part of the planktonic realm that had barely existed before. Their success shows how the Ordovician oceans were filling not only with benthic diversity, but also with organisms occupying the open water. Cephalopods, too, reached new levels of importance. The Ordovician gave rise to long, conical-shelled cephalopods that were among the largest predators of their time. These early relatives of squid and octopus grew to lengths of several metres, cruising the seas in search of trilobites and other invertebrates. Their dominance represents one of the first times a large, actively swimming predator ruled marine ecosystems. The balance of power in the oceans was shifting. Survival now required more than passive defences. Prey evolved thicker shells and more elaborate spines, while predators grew larger and more agile. This interplay foreshadowed the predator-prey dynamics that continue to shape marine life today. Geologically, the Ordovician was also a time of tectonic rearrangements. Volcanic arcs collided with continents, mountain ranges rose, and basins filled with sediments. These events influenced sea levels and nutrient fluxes, feeding into the radiations of life. Ash beds interlayered with fossiliferous sediments provide precise radiometric dates, allowing us to reconstruct Ordovician events with unusual clarity. These volcanic episodes may also have influenced climate, injecting sulfur and carbon dioxide into the atmosphere and contributing to both warming and cooling episodes. The End-Ordovician glaciation, with its sudden shift to icehouse conditions, may have been linked in part to long-term tectonic and volcanic cycles. Even while oceans teemed with invertebrate life, the edges of continents were undergoing subtle but revolutionary change. The first land plants, though tiny and simple, began to creep across moist soils. Their root-like structures increased weathering rates, pulling carbon dioxide from the atmosphere and feeding nutrients into rivers. This greening of the land surface, though nearly invisible compared to the vast marine expansion, was altering the global carbon cycle. By drawing down greenhouse gases, these plants may have played a role in triggering the glaciation that ended the period. If so, their quiet colonization of land indirectly contributed to one of Earth's earliest great mass extinctions. The Ordovician thus illustrates the interconnectedness of Earth systems. Shallow seas nurtured biodiversity, drifting colonies transformed plankton, cephalopods redefined predation, and tiny plants reshaped atmospheric chemistry. Each development seemed local, yet together they remade the biosphere. And when glaciers finally advanced, the intricate web of Ordovician life proved vulnerable to collapse. The haunting thought is that diversity once achieved is never guaranteed. Even in its abundance, life is always balanced on the shifting scales of climate, tectonics, and chance. What happens when plants root themselves into rock? That question brings us into the Silurian, a time between about 444 and 419 million years ago, when life's focus began to shift from the seas to the land. The oceans were still thriving, coral reefs expanding into vast structures filled with invertebrates and fish, but something quiet and unprecedented was unfolding along shorelines and riverbanks. Plants were no longer content to hug damp soils as tiny moss-like mats. They had begun to grow vascular tissues, sturdy stems, and anchoring roots. For the first time, life was digging into rock, splitting it apart grain by grain, drawing nutrients upward and reshaping landscapes that had been barren for billions of years. The Silurian world was recovering from the devastation of the end Ordovician glaciation. As ice sheets retreated and sea levels rose, new shallow marine habitats opened up. Coral and stromatoporoid reefs grew across these continental shelves, creating ecosystems teeming with brachiopods, trilobites, mollusks, crinoids, and early fish. These reefs were not only hubs of biodiversity, but also stabilizers of marine environments, filtering waters and creating gradients of light and shelter. In the seas, jawless fish diversified into a wide array of armoured forms, and the first jawed fish, the ancestors of sharks and bony fishes, appeared. Yet even these changes, monumental as they were, pale compared to what was happening on land. Fossils of Silurian plants such as Cooksonia reveal stems only a few centimetres tall, tipped with sporangia releasing spores. They lacked leaves and true roots, but they had vascular tissues, xylem and phloem, that allowed them to transport water and nutrients internally. This innovation freed them from the absolute dependence on constant wetness. They could grow taller, occupy drier soils, and reach towards sunlight. Their presence marked the beginning of terrestrial ecosystems. By cracking rocks with primitive root-like structures and accelerating chemical weathering, these plants drew carbon dioxide from the atmosphere and released oxygen. Over millions of years, their slow but steady colonization began to alter the global carbon cycle and climate. Alongside plants came the first terrestrial animals. The Silurian fossil record includes early evidence of millipede-like arthropods, tiny creatures that likely fed on decaying plant matter and microbial mats. Simple insects may have been present, scuttling along damp soils. These were not yet the buzzing, flying insects of later ages, but pioneers taking advantage of new food sources on land. Their presence shows that once plants established themselves, animals quickly followed, beginning the intricate partnerships and competitions that still define ecosystems today. This gradual conquest of land must have transformed Earth in ways we can only imagine. For billions of years, the continents had been silent landscapes of bare rock, dunes and microbial crusts. By the late Silurian, green patches dotted shorelines, streamsides and floodplains. Tiny forests of stemmy plants captured sunlight, stabilized soils, and provided food for early arthropods. These ecosystems were fragile and small, but they were the first steps toward the forests and grasslands that would eventually dominate Earth's surface. The Silurian also gave us one of the earliest hints of soil formation. As plants anchored themselves, they trapped organic matter and created microhabitats for fungi and bacteria. This biological weathering began the slow transformation of mineral surfaces into soils, creating reservoirs for nutrients and water. It was an invisible but critical step in Earth's history, for without soils, land plants could never have expanded, and terrestrial ecosystems could not have flourished. By the close of the Silurian, life on land was still in its infancy, but the direction was clear. Plants were adapting to dry environments, arthropods were exploring the new frontier, and ecosystems were beginning to link the fates of continents and oceans. The haunting question is how fragile those first steps may have been. A slight shift in climate, a lack of symbiosis with fungi, or the absence of arthropod decomposers could have halted the greening of the continents. Instead, the Silurian shows us that once life set its roots into stone, it was determined to stay. Another subtle revolution of the Silurian was the partnership between plants and fungi. Fossils and geochemical clues suggest that even the earliest land plants relied on fungal symbiosis to survive. These primitive plants had no true roots, so they formed associations with mycorrhizal fungi, which helped extract nutrients from rock and soil in exchange for sugars from photosynthesis. This cooperation was not a small detail, it was the foundation on which terrestrial life could expand. Without fungi, plants would have struggled to colonize nutrient-poor surfaces. Together they pioneered the transformation of barren landscapes into living systems. The seas, meanwhile, continued their own experiments. Jawed fishes, or gnathostoms, first appear in the Silurian fossil record, including early placoderms with heavy armour plating around their heads. These fishes represent one of the most significant steps in vertebrate evolution, for jaws opened new possibilities in feeding strategies, from grasping prey to chewing plant material. Alongside them, cartilaginous fishes, the ancestors of sharks and rays, were beginning to emerge. Though small and simple compared to their later relatives, these Silurian pioneers marked the first time vertebrates became active predators in the open water, reshaping marine ecosystems just as plants were reshaping land. Coral reefs also reached new levels of complexity in the Silurian. Rugose and tabulate corals, together with stromatoporoid sponges, constructed reef systems that stretched for kilometres. These reefs provided shelter for trilobites, crinoids, brachiopods, and countless other invertebrates. They were early engines of biodiversity, and their expansion stabilised coastlines, buffered waves, and created habitats that nurtured evolutionary innovation. With fish swimming above, corals anchoring below, and invertebrates filling the gaps, Silurian seas resembled modern marine ecosystems in structure, if not in detail. One of the most striking aspects of this period is the gradual knitting together of ocean and land systems. Plants pulling carbon dioxide from the atmosphere influenced climate, while their weathering of rock fed nutrients into rivers and seas. These nutrients enriched coastal waters, fueling blooms of algae and plankton that supported marine food webs. For the first time, the productivity of land and sea were becoming linked, an interconnection that would only deepen as plants expanded. By the end of the Silurian, continents were no longer barren expanses. Though vegetation was still sparse and low to the ground, the coastlines were lined with pioneering plants, the soil stirred by arthropods, and the seas aslave with jawed fish and reef builders. Earth was visibly changing from a world dominated entirely by water into one where land was beginning to share in the story of life. The haunting thought is how fragile those first ecosystems were. A few centimetres of vascular tissue, a simple arthropod crawling from water to soil, these were small steps at the time, yet they were irreversible. From here on, Earth would be both blue and green, a planet of seas and continents bound together by biology. Why risk leaving the ocean behind? That question defines the Devonian, a span from about 419 to 359 million years ago, often called the Age of Fishes, but just as importantly the dawn of forests and the tentative steps of vertebrates onto land. It was a time of radical change, when ecosystems grew in height, depth, and complexity. Fish became astonishingly diverse. Plants colonized the continents with towering trees, and the first tetrapods clambered onto shorelines, beginning a lineage that would eventually lead to every reptile, bird, and mammal. Yet these transformations were not inevitable. They unfolded through a cascade of adaptations, experiments, and extinctions, many of which we still puzzle over today. The seas of the Devonian were home to an extraordinary radiation of fishes. Placoderms, the armoured fish that had begun in the Silurian, dominated coastal waters, some growing to lengths of over 6 metres. The most famous of these giants, Dunkleosteus, had jaws that could slice through bone with terrifying force. Alongside them, cartilaginous fishes, early relatives of sharks, diversified, taking on sleek, fast-moving forms. Meanwhile, bony fishes, both ray-finned and lobe-finned, proliferated across lakes, rivers, and shallow seas. The ray-finned fishes would become the most successful vertebrates of all time, still representing the majority of fish species today, while the lobe-finned fishes gave rise to lungfish and coelacanths, as well as the ancestors of tetrapods. Why lobe-finned fishes? Their fleshy, muscular fins supported by robust bones allowed them to push along the seafloor or navigate shallow, plant-choked waters, where manoeuvrability was essential. Some developed primitive lungs, enabling them to gulp air in stagnant swamps when oxygen levels dropped. These traits were not designed for life on land, but they were pre-adaptations that made landfall possible. Fossils such as Eusthenopteron and Pandrichthys show the gradual strengthening of a limb-like structures, while Tiktaalik, discovered in Arctic Canada, illustrates a remarkable intermediate, with both gills and lungs, scales and ribs, fins and wrist-like joints. Its flat head and mobile neck hint at an animal adapted to peering above water in shallow, vegetation-filled channels. While vertebrates explored shallow habitats, plants transformed the land above them. The Devonian saw the rise of the first true forests, dominated by giant cladoxylopsids, early ferns and lycopsids. These trees grew meters tall, supported by woody tissues and anchored by deep root systems. Forests stabilized soils, shaded rivers, and altered atmospheric chemistry on a massive scale. By drawing down vast amounts of carbon dioxide, they cooled the global climate. Their roots broke down rock, releasing nutrients that washed into seas and triggered algal blooms, reshaping marine ecosystems. For the first time, Earth had landscapes that resembled modern terrestrial environments, with canopies, undergrowth, and soils forming layers of complexity. Forests also created entirely new niches. Arthropods thrived in the leaf litter and on trunks, with evidence of millipedes, centipedes, and early arachnids spreading widely. Insects diversified, though flight was still in the future. The greening of the continents was no longer a thin film of mosses. It was a profound ecological transformation, knitting together land, rivers and seas in a feedback system that changed climate, biogeochemical cycles, and evolutionary trajectories. But with forests came challenges. The burial of organic matter and the drawdown of carbon dioxide may have contributed to cooling trends, and the nutrient wash into seas likely played a role in ecological crises. The late Devonian was punctuated by multiple extinction pulses, sometimes grouped together as one prolonged crisis. Reef systems collapsed, many placoderm lineages vanished, and trilobites suffered heavy losses. The causes remain debated. Climate cooling, ocean anoxia, volcanic activity, and the effects of forest expansion have all been implicated. The Devonian extinctions remind us that evolutionary innovations can carry unintended consequences, reshaping the planet in ways life cannot anticipate. The first tetrapods emerged against this backdrop of change. Fossils such as Acanthostega and Ichthyostega from the late Devonian of Greenland reveal creatures with limbs bearing digits but still tied to water for reproduction. They were more amphibious than terrestrial, probably using their limbs to haul themselves between pools or along swampy banks. They were not conquering land in the way reptiles or mammals later would, but testing the boundaries, experimenting with new modes of locomotion and survival. To imagine them is to picture strange animals with tails, gills and lungs, clumsy on land yet pioneering the first steps into a new domain. The Devonian is thus a story of exploration. Fish into new habitats, plants into forests, arthropods into litter, and tetrapods onto land. It was not a linear march, but a web of experiments, many of which failed. Placoderms, once rulers of the seas, would not survive beyond the Devonian. Most early tetrapod lineages vanished. Entire reef ecosystems collapsed. Yet each loss carved space for new radiations, and the survivors carried forward traits that would define the next chapters of Earth's history. The haunting question is why life chose to risk the land at all. The seas were rich and vast, while land offered desiccation, gravity and exposure. Perhaps shallow, oxygen-poor waters forced innovation. Perhaps predation pressures drove escape into new habitats. Or perhaps it was simply chance, a few lineages stumbling into a niche that proved viable. Whatever the reason, the Devonian shows that evolution often advances by accident, with consequences far beyond what any species could foresee. The forests and tetrapods of this age reshaped Earth forever, turning it from a water world with green edges into a truly terrestrial planet. What kind of world grows dragonflies the size of seagulls? To find out, we step into the Carboniferous, a period stretching from about 359 to 299 million years ago. It was an age when dense swamp forests spread across equatorial regions, oxygen levels in the atmosphere soared, and strange ecosystems produced creatures that seem almost alien today. The Carboniferous has left us with one of its most enduring legacies, immense coal deposits that still fuel human societies. Yet the story of this period is far richer than just fossil fuels. It is about the rise of towering plants, the dominance of amphibians, the appearance of the first reptiles, and the subtle but decisive reorganization of Earth's air and climate. The defining feature of the Carboniferous landscape was the coal swamp. Along low-lying floodplains and deltas, vast forests grew thick with lycopsids, horsetails and giant ferns. Lycopsids such as lepidodendron reached heights of 30 metres, with trunks covered in leaf scars and crowns of narrow foliage. Horsetails, represented today by the modest equisetum, grew into trees more than 10 metres tall. Seed ferns added variety, while true ferns diversified in the understory. These forests thrived in wet environments where rising and falling waters deposited layers of sediment. When trees fell into stagnant swamps, their remains accumulated faster than they could decompose. Over millions of years, compression and heat transformed this organic material into the thick coal seams we mine today. This lush vegetation had planetary consequences. Photosynthesis drew enormous amounts of carbon dioxide from the atmosphere, while burial of plant matter locked away carbon that would otherwise have returned to the air. Oxygen levels rose dramatically, possibly reaching concentrations as high as 35%, far higher than today's 21%. Such oxygen-rich skies created both opportunities and challenges for life. Insects and arthropods, which rely on diffusion of oxygen through tracheal systems rather than lungs, could grow to gigantic sizes. Fossils reveal dragonflies with wingspans of 70 centimetres, millipedes longer than a human, and scorpions as large as a cat. These oversized creatures ruled the swamp forests, their growth fueled by the abundance of oxygen in every breath. But the Carboniferous was not simply a paradise of plants and insects. Amphibians diversified into a wide array of forms, some as large as crocodiles, hunting in rivers and swamps. They were the dominant vertebrates of the time, but their dependence on water for reproduction kept them tied to aquatic habitats. Around this time, the first reptiles appeared. Small lizard-like creatures such as Hylonomous, known from fossilized tree stumps in Nova Scotia, represent the earliest known amniotes. With their shelled eggs, they were no longer dependent on water for reproduction. This innovation opened up new ecological possibilities, allowing vertebrates to colonize drier environments. The reptilian lineage would expand in later ages, but its roots trace back to the Carboniferous. The oceans of this period tell a different story. Reef building had diminished since the Devonian, but marine life remained rich with brachiopods, crinoids, bryozoans, and ammonites. Sharks and early ray-finned fishes diversified, exploring new ecological niches. Yet compared to the lush drama of the coal swamps, the seas of the Carboniferous seem almost steady backdrops to the explosive greening of the continents. It was on land, not in the ocean, that the most transformative innovations of this period occurred. The global climate of the Carboniferous oscillated between warm, humid conditions and cooler intervals. By the late Carboniferous, glaciation spread across the supercontinent Gondwana, lowering sea levels and reshaping habitats. These shifts fragmented swamp forests and may have contributed to a decline in the giant arthropods that had flourished earlier. With less oxygen in later stages, the oversized insects gradually disappeared. Even so, the ecosystems of the Carboniferous had already reshaped the Earth in fundamental ways. The burial of carbon in coal swamps drove atmospheric oxygen to unprecedented levels, influencing fire regimes, animal physiology, and even global climate. The Carboniferous world is both familiar and alien. Forests of towering trees resemble modern ecosystems, yet their architects, lycopsids and seed ferns, are mostly extinct today. Insects buzzed and crawled across the landscape, but at sizes unimaginable in our world. Amphibians thrived as the top predators, while small reptiles quietly pioneered a future that would belong to them. And beneath it all, peat slowly transformed into coal, storing away energy that would one day be unleashed by another primate species millions of years later. The haunting question is whether the Carboniferous was a one-time accident of Earth's history or a natural outcome of evolution. Could the combination of swampy equatorial landscapes, oxygen oversupply and coal formation have unfolded differently? We cannot know for certain. What we do know is that this period left behind a legacy still shaping our world, both in the deep seams of fossil fuel that drive our societies and in the evolutionary pathways of reptiles and insects that continue to dominate today. The Carboniferous shows us how ecosystems can build the very air we breathe, and how fragile that balance can be when climates shift and forests fall. One of the most fascinating consequences of the Carboniferous environment was fire. With oxygen levels so high, the planet became unusually flammable. Even damp vegetation could ignite more easily than it does today, and wildfires likely swept through dry patches of forest whenever lightning struck. Charcoal deposits in Carboniferous rocks are common, testimony to this fiery world. These fires may have acted as a natural check on forest expansion, clearing space for new growth and recycling nutrients back into the soil. Yet they also highlight the precarious balance of the atmosphere. Too little oxygen and large insects could not breathe efficiently. Too much, and the world risked burning uncontrollably. For tens of millions of years, life thrived within this narrow window. Another underappreciated development of the Carboniferous was the complexity of forest canopies. Before this period, terrestrial plants rarely exceeded the height of a human. Now, forests layered themselves into multiple vertical zones, with towering lycopsids, mid-story ferns and ground-level horsetails. This stratification created diverse microhabitats, offering niches for arthropods and small vertebrates. The ecological architecture of modern forests, shade, leaf litter, vertical structure, was first assembled in the Carboniferous. For the animals within it, this was a world of unprecedented opportunities but also of new dangers, as predators could now hunt from multiple levels of the forest. The vertebrate story of the Carboniferous is also one of transition. Amphibians flourished in the swamps, but their permeable skin and reliance on water-bound reproduction limited their expansion. The reptiles that emerged during this time, though modest in size, introduced the amniotic egg, a structure that protected embryos from desiccation and allowed development away from open water. This single adaptation began the slow shift of vertebrate dominance from amphibians to reptiles, a process that would reshape ecosystems in the Permian and beyond. It is striking that the earliest reptiles appear not as apex predators, but as small insect-eating forms, quietly occupying niches that amphibians had overlooked. From such humble beginnings, entire dynasties would rise. Global geography also played its role. During the Carboniferous, the supercontinent Pangaea was assembling. Continents collided, raising mountain belts and altering climate patterns. The equatorial regions where coal swamps thrived were humid and stable, while higher latitudes experienced cooler, drier conditions. The spread of glaciations across Gondwana late in the period caused sea levels to fall, fragmenting the swamp forest that had dominated earlier. This fragmentation may have accelerated evolutionary turnover, forcing plants and animals to adapt to patchier habitats. In many ways, the Carboniferous was both a pinnacle of lush, oxygen-rich abundance and the beginning of its unravelling. When we look back on this age, the haunting question remains, could such a world exist again? The towering leucopsids, giant dragonflies, and oxygen-heavy skies seem fantastical, yet they were real. Their disappearance reminds us how quickly global balances can shift. Forests that built the air we breathe eventually collapsed, reshaping life's trajectory. What endures from the Carboniferous is not only coal, but also the blueprint for complex terrestrial ecosystems, forests, soils, canopies, and the vertebrates that would one day inherit them. What does near-total collapse look like? To answer that, we step into the Permian, a chapter of Earth's story spanning from about 399 to 252 million years ago. It began with triumph and ended with catastrophe. The Permian opened as a time of consolidation, when continents that had wandered for eons finally fused into the supercontinent Pangaea. It closed with the most devastating extinction event in Earth's history, wiping out more than 90% of marine species and a great share of terrestrial life. Between those bookends stretched a world of deserts, reptilian innovations, and volcanic cataclysms whose echoes still shape the planet today. The geography of the Permian is unlike anything before or since. Pangaea was an immense landmass stretching from pole to pole, wrapped by a single global ocean called Panthalassa. Its sheer size created extremes in climate. The interior of the supercontinent was far from moderating oceanic influences, leaving vast, arid deserts where seasonal temperatures soared by day and plunged by night. Along coastal margins and river valleys, life was richer, but the overall picture was one of extremes, lush oases alternating with barren wastelands. These environmental contrasts drove evolutionary innovation, forcing plants and animals to adapt to conditions of scarcity, drought, and unpredictability. On land, the stage was dominated increasingly by reptiles. The amniotic egg, pioneered in the Carboniferous, now revealed its full power. Reptiles no longer needed to lay their eggs in water, freeing them from aquatic constraints. They diversified into numerous lineages, some herbivorous, some carnivorous, ranging from small lizard-like forms to massive predators. Among them were synapsids, often nicknamed mammal-like reptiles, though they were not reptiles at all but the distant ancestors of mammals. Creatures such as Dimetrodon prowled floodplains, their iconic sails possibly used for thermoregulation or display. Later synapsids evolved into more advanced therapsids, with differentiated teeth and more efficient limb postures. They hint at the mammalian blueprint that would eventually emerge, though in the Permian they were only experimenting with possibilities. Plants too reshaped landscapes. Glossopteris, a seed fern, spread widely across Gondwana, leaving vast fossilised leaf beds that now help us trace continental drift. Gymnosperms such as conifers began to diversify, adapting to drier interiors of Pangaea with seeds encased in protective coverings. These plants thrived where spore-bearing ferns struggled, pushing terrestrial vegetation toward the forms still familiar today. By the late Permian, forests of conifers, cycads, and seed ferns dotted the supercontinent, resilient against shifting climates. Marine life, however, faced growing stresses. Brachiopods and crinoids, once dominant, began to decline. Reefs constructed by sponges and algae faltered, leaving marine ecosystems less stable. Ammonoids, relatives of squid and octopus, flourished in diversity, their coiled shells marking evolutionary experiments across the seas. But beneath the surface, unseen pressures were building. Ocean chemistry was subtly shifting, possibly due to changes in circulation, nutrient cycles, and the gradual leakage of volcanic gases into the atmosphere. The true catastrophe struck at the end of the Permian. Around 252 million years ago, an immense volcanic province erupted in what is now Siberia, known as the Siberian Traps. Over the course of hundreds of thousands of years, fissures bled lava across millions of square kilometres, one of the largest volcanic events in Earth's history. With the lava came gases, carbon dioxide, sulfur dioxide, methane, poured into the atmosphere in staggering quantities. These emissions triggered runaway greenhouse warming, acidified oceans, and stripped oxygen from marine waters. Ocean anoxia spread, leaving vast stretches of the sea uninhabitable. On land, intense warming and acid rain devastated ecosystems while wildfires raged across dry forests. The toll was unprecedented. Coral reefs vanished. Trilobites, survivors for hundreds of millions of years, finally disappeared entirely. Insects suffered their only known mass extinction. Synapsids, once dominant on land, dwindled to a few lineages. An estimated 90% of marine species and 70% of terrestrial vertebrates perished. For tens of millions of years afterward, Earth's recovery was slow and halting, ecosystems fragile and diversity low. It was as close as life has come to starting over without being completely erased. The Permian story is haunting not only for its devastation, but also for its lessons. It reminds us that Earth is a system of delicate balances. Continental arrangements, volcanic activity, atmospheric gases, and biological innovations all interact in feedback loops. When those loops are pushed too far, collapse follows. And yet, even after the Great Dying, life endured. A few lineages of synapsids would eventually give rise to mammals. Archosaurs, ancestors of crocodiles and dinosaurs, would take advantage of empty niches. Plants would recolonize scorched soils. Out of near-total collapse came new opportunities, though the cost was almost everything. The haunting question is why Earth teetered so close to total lifelessness, yet did not tip over completely. Was survival inevitable, driven by microbial resilience in deep oceans and soils, or was it a stroke of chance that enough species persisted? We cannot know for sure. What we do know is that the Permian stands as the starkest reminder that life's continuity is never guaranteed. The Great Dying was not simply an ending. It was a brutal reset, shaping the course of all evolution that followed. Who fills the vacuum after life's worst disaster? To answer that, we turn to the Triassic, spanning from about 252 to 201 million years ago. It began in the shadow of catastrophe, with ecosystems stripped bare by the Great Dying of the Permian. More than 9 out of 10 marine species and most land animals had been extinguished. The survivors faced a near-empty world, a biological blank slate. Over the course of 50 million years, those survivors rebuilt Earth's ecosystems, experimenting with new forms and lineages that would dominate the next chapters of history. The Triassic was a crucible, a period of low diversity but high innovation, when both the first dinosaurs and the first mammals appeared, and the seas gave rise to formidable reptiles that redefined what it meant to be a marine predator. The early Triassic was stark and bleak. Fossil assemblages show ecosystems dominated by a handful of species, particularly the hardy Lystrosaurus, a pig-sized therapsid that may have accounted for the majority of land vertebrates in some regions. With few competitors and an ability to burrow through harsh conditions, Lystrosaurus epitomized survival rather than triumph. On land, recovery was painfully slow. Plants regrew unevenly, with leucopsids, seed ferns, and early conifers returning to patchy dominance. In the oceans, microbial mats spread across seafloors where reefs had collapsed, forming structures called stromatolites in shallow waters. For millions of years, these microbial systems were the default marine ecosystems, reminders of a much more ancient Earth. Gradually, however, diversity began to rise again. Therapsids, though reduced, diversified into new herbivores and carnivores. Archosaurs, an emerging group that would eventually produce crocodiles, pterosaurs, and dinosaurs, expanded in range and form. In rivers and lakes, amphibians such as temnospondyls reached large sizes, sometimes rivaling crocodiles. Marine reptiles appeared in the form of ichthyosaurs, streamlined predators that resembled dolphins though they were unrelated, and nothosaurs, long-necked hunters of fish. These groups exploited open niches in the seas, rapidly achieving success as apex predators. The Triassic was a time when reptiles were testing the boundaries of form, both on land and in water. The rise of dinosaurs was not immediate. Early forms such as Eoraptor and Herrerasaurus in South America were small, bipedal predators, living in ecosystems still dominated by other archosaurs like Rauisuchians, large quadrupedal carnivores. But dinosaurs had traits that gave them long-term advantages: upright postures, efficient breathing systems, and adaptability across climates. By the late Triassic, they were beginning to diversify into herbivores and carnivores, setting the stage for their dominance in the Jurassic. Alongside them, the first mammals quietly appeared. Descended from therapsid ancestors, these early mammals were tiny, likely nocturnal, insectivorous creatures with differentiated teeth and fur-like coverings. They did not rule the Triassic world, but they occupied small, safe niches, surviving under the feet of larger reptiles. Their story was one of patience, waiting in the margins until later opportunities arose. Marine ecosystems also flourished with innovation. Ichthyosaurs evolved rapidly, from lizard-like beginnings into fully aquatic forms with dorsal fins and tail flukes. Some grew enormous, rivaling whales in later periods. Nothosaurs gave rise to plesiosaurs by the end of the Triassic, with their distinctive long necks and flippered bodies. These marine reptiles filled the ecological roles once dominated by fish and sharks, demonstrating how quickly life could reinvent oceanic predators. Pangaea, the supercontinent, still dominated Earth's geography. Its immense size produced extreme climate patterns, with vast deserts stretching across the interior and seasonal monsoons along coastal regions. Fossil footprints in arid basins tell us of herds of early archosaurs travelling across dune fields, while river deposits preserve amphibians and fish from wetter environments. This continental arrangement limited shallow marine habitats, but it facilitated the spread of terrestrial animals across vast distances, linking ecosystems from pole to pole. The Triassic ended as it began, with extinction. Around 201 million years ago, massive volcanic eruptions associated with the breakup of Pangaea released vast amounts of carbon dioxide, warming the climate and acidifying the oceans. Many archosaurs, amphibians, and marine reptiles vanished. Dinosaurs, however, survived and thrived, inheriting the vacant niches. Mammals also endured, remaining small but persistent. Once again, mass extinction reshaped the trajectory of life, elevating some lineages and erasing others. The Triassic is haunting because it shows both the fragility and resilience of life. From the bleak aftermath of the Great Dying, ecosystems rebuilt slowly, experimenting with reptiles that conquered both land and sea, while mammals and dinosaurs began parallel journeys that would shape the rest of Earth's history. The question that lingers is whether recovery after catastrophe always breeds innovation. Did the Triassic produce dinosaurs and mammals because survival demanded it, or because chance gave them space to expand? We cannot be certain. What we can say is that the Triassic was a rebirth, a period of fragile recovery that gave us the ancestors of the great stories yet to come. One of the most overlooked stories of the Triassic is the rise of the skies. It was during this period that the first vertebrates took to the air. Pterosaurs, with their membranous wings stretched between elongated fingers, emerged by the late Triassic. The earliest known forms, like Preondactylus and Eudimorphodon, were small, insect-eating flyers with long tails and toothed jaws. They were clumsy compared to later pterodactyloids, but they mark the first time a vertebrate conquered powered flight. Insects had already ruled the air for hundreds of millions of years, but the arrival of pterosaurs opened a new dimension for vertebrate ecology. From this experiment would come a lineage that endured until the end of the Cretaceous, reshaping food webs with aerial predation. On land, another predator lineage dominated before dinosaurs rose, the Rauisuchians. These massive archosaurs walked with upright limbs and resembled crocodile-like hunters, some reaching lengths of 7 to 9 meters. Fossilized trackways and skeletons show they were apex predators across Pangaea, preying on early dinosaurs, synapsids, and other reptiles. Their reign was relatively brief, extinguished at the end of the Triassic, but for millions of years they were the true rulers of the land, not dinosaurs. The balance of ecosystems was far from inevitable. Had Rauisuchians endured, the age of dinosaurs might never have dawned. Plants too continued to evolve during the Triassic. Conifers diversified further, spreading into arid environments and providing stable food sources for herbivores. Cycads and ginkgophytes expanded, their tough leaves adapted to drought. These gymnosperms were the architects of the first great reptile-dominated ecosystems, sustaining herbivores like early sauropodomorph dinosaurs and dicynodont therapsids. The rise of seed plants marked a permanent shift toward vegetation, better adapted to the fluctuating climates of Pangaea, where long dry seasons and erratic rainfall demanded resilience. The Triassic also witnessed the expansion of burrowing lifestyles. Fossil burrows reveal communities of small reptiles and mammal relatives living underground to escape extreme heat and drought. These burrows preserved rare traces of behaviour, such as multiple animals sharing the same chamber, suggesting that even in these early times, sociality and cooperation may have been survival strategies. Burrowing would become a recurrent solution in evolutionary history, but its importance in the Triassic underscores how harsh conditions shaped innovation. As the period drew to a close, massive volcanic activity at the Central Atlantic Magmatic Province heralded the end Triassic extinction. Lava flows covered millions of square kilometres, releasing vast pulses of carbon dioxide that warmed the climate and destabilised ecosystems. Marine reptiles, Rauisuchians, and many amphibians perished. Dinosaurs, small and adaptable at the time, managed to endure, and in the wake of devastation they expanded into dominance. Mammals also survived, clinging to nocturnal, small-bodied lifestyles. In this way, the Triassic ended much as it began, with catastrophe clearing the way for survivors to define the next age. The haunting question of the Triassic is whether life always rebounds from collapse with greater innovation, or whether this period was unique in how it forged the lineages that would shape the Mesozoic. We know only that from a world nearly emptied by the Permian, the Triassic gave rise to dinosaurs, mammals, pterosaurs, and marine reptiles. It was a rebirth forged in hardship, proof that even after near-total loss, life is never finished experimenting. Why did dinosaurs reach such staggering sizes? To explore that question, we step into the Jurassic, a period that stretched from about 201 to 145 million years ago. The Triassic had been a time of recovery and experimentation, but the Jurassic brought flourishing abundance. Dinosaurs grew from small survivors into giants that reshaped entire ecosystems. Sauropods, with their colossal necks and towering forms, became the largest land animals ever to walk the Earth. Theropods, their predatory counterparts, reached imposing sizes and diversified into countless forms. The first birds took to the skies, while forests of conifers, cycads and ferns created lush backdrops for this unfolding drama. The world itself was changing. Pangaea began to break apart in the early Jurassic, splitting into northern Laurasia and southern Gondwana. This tectonic fragmentation created rift valleys, shallow seas and new coastlines, stimulating biodiversity. Climates grew more humid than in the arid Triassic, encouraging expansive forests. Fossilised pollen and wood reveal conifer-dominated landscapes interspersed with cycads, Bennettitalians, and ginkgos. Ferns carpeted the understory, creating a green world more recognisable to modern eyes than the spore-dominated landscapes of earlier eras. This abundance of plant biomass provided the fuel for gigantic herbivores to thrive. Sauropods exemplify this transformation. Genera such as Brachiosaurus, Diplodocus, and Apatosaurus reached lengths of 20 to 30 metres, with masses rivaling modern whales. Their success rested on a suite of adaptations. Long necks allowed them to browse high in the canopy, or sweep wide arcs across vegetation without moving their massive bodies. Lightweight but strong vertebrae reduced the burden of such size, while efficient air sac respiratory systems, inherited from earlier archosaurs, ensured that oxygen delivery kept pace with metabolic demands. Herd behaviour may have provided protection against predators, while sheer size itself offered safety. To stand next to such a creature, had we the chance, would have been to confront living architecture, animals so immense that they reshaped forests simply by walking through them. Predators grew in parallel. Theropods such as Allosaurus dominated the Jurassic as apex hunters. Fossil evidence, including tooth marks on sauropod bones, suggests they hunted or scavenged the giants that shared their landscapes. Smaller theropods diversified into niches ranging from fish-eaters to agile pack hunters. The origins of birds trace back to this time, with feathered dinosaurs such as Archaeopteryx revealing the gradual transition from ground-dwelling theropods to creatures capable of powered flight. Feathers had likely evolved earlier for insulation or display, But in the Jurassic, they became tools for gliding and flying, opening a new ecological dimension. Marine environments flourished with equally spectacular life. Pliosaurs, short-necked plesiosaurs with massive jaws, hunted ammonites and fish in coastal seas, while long-necked plesiosaurs exploited different feeding strategies. Ichthyosaurs, streamlined and dolphin-like, remained dominant in open waters, reaching immense sizes and giving live birth to their young. Ammonites themselves radiated into countless forms, their coiled shells a common fossil hallmark of Jurassic strata. Coral reefs returned in abundance, building new marine ecosystems after their earlier decline. The Jurassic was also a period of geological dynamism. Volcanic activity accompanied rifting continents, shaping local climates and providing fertile soils for forests. Rising sea levels created broad, shallow seas across continental margins, preserving rich fossil assemblages such as those in the Solnhofen limestone of Germany, which famously yielded Archaeopteryx. These fine-grained deposits captured delicate details, from feather imprints to the bodies of pterosaurs and marine creatures, offering rare glimpses into Jurassic ecosystems. But why such gigantism? The answer remains uncertain. Some argue that high levels of atmospheric oxygen and carbon dioxide encouraged lush plant growth and supported large body sizes. Others point to sauropods' unique physiology, with efficient lungs and lightweight skeletons that allowed them to grow larger than any other land animals. Still others emphasize ecological opportunities. With predators unable to easily kill fully grown giants, sauropods could thrive in herds, eating vast quantities of vegetation without fear. Whatever the cause, the Jurassic was the only time in Earth's history when land animals reached such monumental proportions, a biological experiment unmatched before or since. The end of the Jurassic did not bring sudden catastrophe. Rather, it marked transitions. Dinosaurs diversified into even more forms that would dominate the Cretaceous. Birds took firmer hold in the skies, refining flight. Mammals remained small and nocturnal, but they diversified quietly in the shadows of giants, experimenting with niches that would one day serve them well. Marine reptiles continued to rule the seas, while ammonites proliferated as both prey and predator. The haunting question of the Jurassic is why gigantism has not returned. If sauropods could evolve to such immense scales, then why not again? Perhaps the answer lies in the particular combination of climate, vegetation, physiology, and predator-prey dynamics that defined the Jurassic, and that may never align so precisely again. The Age of Giants was not just a product of evolution, but of Earth's unique moment in time. The dinosaurs of the Jurassic remind us that size itself can be an evolutionary strategy, but one that depends on conditions we may never see repeated. The skies above the Jurassic forests were not empty. Pterosaurs, which had first appeared in the late Triassic, reached remarkable diversity during this period. Some were small insect hunters with long tails and delicate wings, while others, like Rhamphorhynchus, patrolled coastal waters, diving for fish with their toothed beaks. Their wings, formed from membranes stretched over elongated fingers, gave them a flight dynamics unlike any bird. They filled ecological roles that would later be occupied by bats and seabirds, but their evolutionary path was uniquely their own. The presence of both pterosaurs and early birds in the skies shows how quickly the air became a contested environment once vertebrates learned to master it. Jurassic ecosystems also reveal fascinating interactions between plants and animals. The spread of conifer-dominated forests provided abundant food for herbivorous dinosaurs, but these trees also evolved defences, such as tough needles and resin, to deter feeding. Cycads and ginkgos contributed to the landscape with nutrient-rich seeds, which may have attracted smaller vertebrates and early mammals. Fossilised coprolites, dinosaur droppings, contain plant fragments that give us clues about diet and digestion. They suggest that sauropods consumed vast amounts of foliage without chewing, relying on massive guts and microbial fermentation to break down their food. This strategy, coupled with near-constant feeding, may explain how such giants maintained their size. One of the most striking fossil sites from this era, the Morrison Formation of North America, preserves a vivid record of Jurassic life. Here, paleontologists have uncovered herds of sauropods like Apatosaurus and Diplodocus, alongside predators such as Allosaurus and Ceratosaurus. Trackways show patterns of movement that hint at social behaviour, sauropods travelling in groups, perhaps protecting their young from predation. Fossilised nesting sites add to this picture, suggesting that some dinosaurs laid eggs communally, though parental care remains uncertain. These glimpses into behaviour remind us that dinosaurs were not just skeletons, but living animals with social dynamics and strategies for survival. The oceans, too, tell stories of adaptation and innovation. Ammonites, with their spiral shells, developed intricate suture patterns that may have strengthened their shells against predation or environmental pressure. Their rapid evolution makes them excellent markers for dating Jurassic rocks, but it also reflects the intense arms race of the time. Ammonites were prey for ichthyosaurs and pliosaurs, yet their resilience and diversity suggest they were among the most successful invertebrates ever to live. By the close of the Jurassic, ecosystems were more complex than at any earlier point in Earth's history. Giants roamed the land, predators ruled sea and sky, plants covered continents with deep forests, and birds had just begun their evolutionary flight. The haunting question is whether such a balance could have lasted indefinitely had it not been disrupted. The Jurassic shows us what happens when life seizes every opportunity, expanding into every niche and pushing body plans to extremes. It was an age of abundance, but like all ages it was destined to end, giving way to new experiments and eventually new catastrophes. What happens when flowers bloom under dinosaurs' feet? That question guides us into the Cretaceous, a period lasting from about 145 to 66 million years ago, a time when Earth's ecosystems reached extraordinary richness and complexity before being struck by one of the most famous catastrophes in history. Dinosaurs, already diverse, flourished into countless specialised forms. Mammals remained small but steadily expanded their ecological roles. The seas teemed with reptiles, ammonites, and new types of fish. Yet the most transformative change of all may not have been in animals but in plants, as flowering plants, angiosperms, emerged and spread, reshaping landscapes, diets, and the very rhythms of ecosystems. The Cretaceous was a paradox, a paradise of innovation and diversity, cut short by a single, devastating asteroid impact that ended the age of dinosaurs. The Cretaceous world looked strikingly modern in many ways. Continents continued to drift apart as the breakup of Pangaea progressed. Shallow inland seas flooded continental interiors, such as the Western Interior Seaway that split North America in two. Warm climates extended to high latitudes, supporting polar forests where dinosaurs roamed in months of near darkness. Volcanic activity and shifting seaways created dynamic coastlines, promoting diversity both on land and in the oceans. Fossil evidence shows an Earth bustling with life across every environment, from equatorial jungles to polar woodlands, from coral reefs to open oceans. Dinosaurs reached new heights of diversity. Titanosaurs, among the last great sauropods, became the dominant long-necked herbivores, some stretching to lengths of 30 metres. Ornithischians, such as hadrosaurs, developed sophisticated chewing systems, grinding tough plants with batteries of teeth. Ceratopsians, with their frills and horns, filled herds across the Cretaceous plains. Carnivorous theropods range from sleek dromaeosaurs, the raptors, to the colossal Tyrannosaurus rex, one of the largest terrestrial predators ever to evolve. The variety of forms was staggering, with dinosaurs adapted to every niche, from swamp-dwelling giants to agile pack hunters. Yet beneath their feet, a quieter revolution unfolded. The first flowering plants appeared early in the Cretaceous, small and unassuming, but they carried evolutionary advantages that transformed ecosystems. Unlike conifers and cycads, angiosperms enclosed their seeds in fruits and developed flowers to attract pollinators. They reproduced quickly and spread into diverse habitats. Insects responded with new specializations, evolving alongside flowers to become pollinators. Bees, butterflies, and beetles expanded their roles, creating intricate webs of coevolution. By the end of the Cretaceous, flowering plants dominated many landscapes, providing new food sources for herbivores and reshaping the structure of ecosystems. The seas of the Cretaceous were equally dynamic. Marine reptiles remained apex predators. Mosasaurs, gigantic lizards adapted to the ocean, rose to dominance late in the period, some growing over 15 metres long. Plesiosaurs, with long necks or massive jaws, hunted fish and ammonites. Ichthyosaurs, once abundant, declined and disappeared by the mid-Cretaceous, perhaps victims of changing ocean conditions. Ammonites, however, flourished, their diverse shells marking every stage of the period. Coral reefs, populated with new species, supported fish that were increasingly modern in appearance, foreshadowing today's oceanic ecosystems. Birds, too, diversified dramatically. Descended from theropod dinosaurs, they evolved a variety of forms, from toothed seabirds to perching species. Some lineages, such as Hesperornis, adapted to flightless penguin-like lifestyles, swimming through seas with powerful legs. Others filled forest canopies, feeding on seeds and insects. The Cretaceous skies were a mix of pterosaurs, some gigantic with wingspans over 10 metres, and early birds exploring every ecological niche. This was a world where the air itself was contested territory, a preview of the dynamic skies that would follow after the dinosaurs were gone. The late Cretaceous world seemed stable, abundant, and resilient. Yet beneath the surface, subtle stresses brewed. Volcanism in India began to produce the vast lava flows known as the Deccan Traps, releasing greenhouse gases into the atmosphere. Sea levels fluctuated, climates shifted, and ecosystems adapted. Still, nothing foreshadowed the sudden catastrophe to come. Around 66 million years ago, an asteroid estimated at 10 kilometers across struck the Yucatan Peninsula of present-day Mexico, creating the Chicxulub crater. The impact released energy equivalent to billions of nuclear bombs, igniting wildfires, producing tsunamis, and sending dust and aerosols into the atmosphere. The aftermath was swift and brutal. Sunlight was blocked, photosynthesis faltered, and food chains collapsed. Dinosaurs that had dominated Earth for over 160 million years perished, with only their avian descendants surviving. Pterosaurs vanished. Ammonites, so abundant for hundreds of millions of years, were extinguished. Marine reptiles like mosasaurs and plesiosaurs disappeared. Mammals, small and adaptable, endured the chaos, as did birds and certain reptiles. The Cretaceous ended in devastation, but it also opened the door for the Cenozoic, when mammals would rise to prominence. The haunting question of the Cretaceous is why flowers bloomed only then, so late in Earth's history. Did it require the right pollinators, the right climate, or a chance mutation? Their emergence coincided with the peak of dinosaur diversity, intertwining the destinies of plants, insects, and reptiles. And the final catastrophe raises another question. If the asteroid had missed, would dinosaurs still dominate today, with mammals remaining in the shadows? The Cretaceous reminds us how fragile abundance can be, and how chance can redirect the entire course of life's story. What thrives when reptiles fall? The answer lies in the Paleogene, spanning from about 66 to 23 million years ago, the first chapter of the Cenozoic and the dawn of the age of mammals. In the wake of the asteroid that ended the Cretaceous, the Earth was stripped of its giants. Dinosaurs were gone, marine reptiles had vanished, ammonites had disappeared, and even pterosaurs had failed to survive. What remained was a planet with vacant niches, ecosystems desperate for new players, and a biosphere adjusting to a radically altered climate. Into this void stepped mammals, creatures that had lingered in the shadows of dinosaurs for more than 100 million years. They now expanded in size, form, and behaviour, transforming from small nocturnal insect eaters into elephants, whales, primates, and carnivores. The Paleogene was the age when mammals inherited the Earth, but their journey was neither smooth nor inevitable. The earliest Paleogene landscapes bore scars of catastrophe. Fossil deposits near the Cretaceous-Paleogene boundary show fern spikes, layers dominated by spores of opportunistic plants that rapidly colonised devastated land. Ecosystems rebuilt step by step, with plants re-establishing first, followed by insects, birds, and mammals. At the start, mammals were small, rarely exceeding the size of a modern cat, but their evolutionary engines ran quickly in the absence of dinosaur competition. Within a few million years, new forms appeared: hoofed herbivores, carnivorous predators, climbing primates, and burrowing specialists. Diversity exploded, not because of one lineage but across many. Marsupials spread in South America and Australia, placental mammals diversified globally, and multituberculates, an ancient group, held on before eventually fading away. The Paleocene, the first epoch of the Paleogene, was a time of experimentation. Mammals such as Pantolambda and Coryphodon grew into medium-sized herbivores, while carnivorous groups like creodonts hunted across forests and plains. Primates began their story here, small tree dwellers with grasping hands and stereoscopic vision. The world was still heavily forested, with warm climates extending even into polar regions. Crocodiles and turtles flourished in northern latitudes, and palm-like vegetation reached toward the Arctic Circle. It was a greenhouse world, lush and humid, where mammals tested their potential. Then came the Paleocene-Eocene thermal maximum. About 56 million years ago, a brief but intense global warming event triggered by massive releases of carbon, possibly from methane hydrates or volcanic activity. Temperatures spiked, polar ice vanished, and tropical ecosystems spread toward the poles. Mammals responded with rapid evolutionary shifts, dispersing across continents through warm corridors. Modern orders such as primates, horses, and even-toed ungulates appeared or diversified during this interval. Fossils from Wyoming and Europe reveal small horses like Eohippus, primates such as Tailhardina, and bats taking flight for the first time. This thermal maximum shows how climate can drive both crisis and opportunity, reshaping evolutionary paths in just a few 100,000 years. The Eocene continued the trend of diversification. Whales evolved from land-dwelling ancestors into fully aquatic giants. Early forms like Ambulocetus still walked on land but swam with powerful limbs, while later genera such as Basilosaurus stretched over 15 meters long and lived entirely in the ocean. Carnivores split into lines that would lead to cats, dogs, and bears. Herbivores grew larger, with titanotheres and brontotheres roaming plains. Forest canopies flourished with new angiosperms, and insects adapted alongside them, co-evolving as pollinators. Birds diversified as well, some reaching immense sizes, such as the flightless terror birds of South America, apex predators that dominated local ecosystems. By the Oligocene, beginning about 34 million years ago, climates cooled again. Ice sheets expanded in Antarctica, sea levels fell, and forests gave way to more open landscapes. Mammals responded with new adaptations for grazing and running. Horses developed higher crowned teeth suited for tougher vegetation, while antelope-like forms appeared across Eurasia. Apes and monkeys diverged within the primate lineage, spreading through Africa and Asia. Carnivores refined their strategies, with nimrovids and early true cats becoming more specialized hunters. Marine mammals also adapted, with the ancestors of seals and walruses beginning their transition to aquatic life. The Paleogene was also a story of shifting continents. India collided with Asia, uplifting the Himalayas. South America drifted in isolation, fostering unique marsupial and ungulate lineages. Australia began to separate, carrying marsupials with it. These movements influenced ocean currents and climates, gradually cooling the planet and setting the stage for later ice ages. The world was becoming more modern in appearance, with recognizable mammals, flowering plants, and ocean systems. The haunting question of the Paleogene is whether mammals would have thrived without the asteroid. Were their success and diversity inevitable given their adaptability, or was it the sudden removal of dinosaurs that opened the door? We cannot know. What we do see is that mammals seized the opportunity with astonishing speed, transforming a post-catastrophe world into one of innovation and resilience. The Paleogene shows us that life does not simply recover after disaster, it reinvents itself. Out of ashes came forests, out of small survivors came giants, and out of chance came the foundations of our own lineage. One of the less obvious but critical changes of the Paleogene was the restructuring of ecosystems from top to bottom. In the Cretaceous, ecosystems had been vertically organised around dinosaurs, with immense herbivores shaping vegetation and colossal predators enforcing balance. With those animals gone, a vacuum opened in the food web. The first large Paleogene mammals did not simply replace dinosaurs, they built new dynamics. Instead of herds of sauropods clearing forests, browsing mammals and smaller-bodied herbivores diversified feeding strategies. Mixed woodlands and open spaces encouraged selective feeders, from leaf-browsing primates in the canopy to grazing herbivores on the ground. Predation too diversified, with carnivores ranging from ambush specialists to pursuit hunters. This shift produced ecosystems that looked more like the layered webs we see today, rather than the dinosaur-dominated systems of the Mesozoic. The Paleogene also redefined migration on a planetary scale. With the breakup of Pangaea well advanced, mammal lineages spread along new land bridges whenever climates allowed. Fossils show camels, horses and primates dispersing between North America and Eurasia when warming opened the Arctic routes. South America remained isolated for much of the Paleogene, producing endemic lineages such as notungulates and litopterns, groups now long extinct but once as diverse as horses and deer. Africa too harboured unique faunas that would later merge with Eurasian lineages. The constant push and pull of isolation and reconnection created a patchwork of evolutionary experiments, many of which vanished when continents collided again. Birds were another set of winners in the Paleogene. With pterosaurs gone, they expanded dramatically. Some evolved into small seed-eating songbirds, others became apex predators. In South America, giant terror birds such as Phorus racos reached heights of 3 meters, chasing down prey with powerful beaks. In Europe, similarly oversized predatory birds filled niches left empty by reptiles. Waterfowl, raptors and seabirds diversified, producing many of the forms familiar today. The skies of the Paleogene were more varied than they had been since the time of pterosaurs, shaping both terrestrial and aquatic ecosystems. Climate remained a restless force throughout the Paleogene. After the warmth of the early epochs, the expansion of Antarctic ice sheets in the Oligocene triggered new feedback loops in ocean circulation. Cold currents strengthened, nutrient flows changed and ecosystems adjusted. Some lineages thrived in the cooler, more seasonal conditions, others dwindled. Forests thinned in places, giving way to grassier environments, though true grasslands would not dominate until later in the Neogene. What we see in the Paleogene is the beginning of a long trend toward climates more variable and challenging, a prelude to the ice ages of the Quaternary. The haunting question of this period is not only why mammals succeeded, but why they diversified so quickly into so many forms. Was it simply ecological opportunity, or did their small size, warm-blooded physiology, and varied diets already prepare them for dominance? We may never know the exact balance of chance and inevitability. What is clear is that the Paleogene was the crucible in which the modern biosphere was forged. By the time it ended, the outlines of today's ecosystems, predators, grazers, forests, and seas were already in place. It was no longer the world of dinosaurs, but it was not yet ours. It was a world in transition, brimming with potential, and still holding its secrets in stone. How do modern ecosystems take shape? To answer that, we step into the Neogene, stretching from about 23 million years ago to 2.5 million years ago. It is in this time that the world begins to look uncannily familiar, not in the fine details of species or the arrangement of continents, but in the overall patterns of climate, vegetation and animals. The Neogene marks the spread of grasslands, the rise of modern grazing and predatory lineages, and the slow but momentous emergence of apes and early hominins. In these millions of years, the Earth transforms from a warm, forested world into one where open landscapes dominate, and where the ancestors of humans start their hesitant steps toward a destiny none of them could have foreseen. The Neogene begins with the Miocene epoch, a time of both continuity and innovation. Forests still blanket large regions, and the diversity of mammals remains high, building on the foundations laid in the Paleogene. But climates are shifting. Global cooling, already underway in the Oligocene, accelerates. Antarctica, firmly seated over the South Pole, accumulates vast ice sheets that reshape sea levels and ocean currents. These currents, including the strengthening of the Antarctic circumpolar current, isolate the continent in a swirl of frigid waters and lock Earth into a pattern of recurring ice growth. This cooling trend favours new ecosystems. Trees retreat in many regions, making way for expanses of grasslands and savannas. Grasses themselves, though ancient in origin, spread aggressively during the Miocene, reshaping not only landscapes but also evolutionary pressures. Grazers adapted to the abrasive, silica-rich blades of grass, evolving high-crowned teeth resistant to wear. Horses, antelopes and rhinoceroses became emblematic of these changes, their bodies fine-tuned for running across open plains. Predators followed suit. Cats, hyenas and canids honed their speed and stamina, transforming hunting strategies into the forms we recognise in today's carnivores. These co-evolutionary dynamics made the Miocene plains arenas of endurance and agility, replacing the dense forest habitats that had once concealed predator and prey alike. Yet forests did not vanish entirely. In tropical belts, woodlands remained refuges of diversity. It is here that primates diversified into both monkeys and apes. Great apes, including lineages leading to gorillas, chimpanzees and humans, trace their roots to Miocene forests. Fossils of species like Proconsul and Dryopithecus reveal early experiments in ape anatomy, from flexible shoulders suited for climbing to larger brains hinting at more complex behaviours. These apes did not look like us, but they carried the seeds of features that would eventually define our lineage. The Miocene was in many ways the laboratory where primates tested paths toward intelligence and adaptability. One of the most profound tectonic events of the Neogene was the collision of continents. India continued its relentless push into Asia, further uplifting the Himalayas and intensifying monsoon systems. In the Americas, the northward drift of South America eventually brought it into contact with North America, though the final closure of the Isthmus of Panama would come later in the Pliocene. These tectonic rearrangements altered not just geography, but also ocean circulation and climate. Shifts in rainfall, temperature and habitats influenced evolutionary trajectories across multiple continents, demonstrating again that the Earth's surface and its biosphere are inseparably linked. Marine life too underwent profound changes. The Neogene oceans hosted familiar groups. Whales diversified further, seals and sea lions colonized coastlines, and sharks adapted to new prey. Coral reefs re-established themselves after earlier declines, anchoring complex marine ecosystems. Ocean circulation changes driven by tectonics and ice growth fostered new productivity zones where plankton thrived. These plankton blooms supported marine food chains that looked strikingly like modern systems, from small fish to apex predators. The Pliocene, beginning about 5 million years ago, sharpened these trends. Grasslands expanded further, especially in Africa, setting the stage for a crucial evolutionary shift. In this changing environment, some primates left the safety of trees and began to walk upright. Fossils such as Ardipithecus and Australopithecus testify to the tentative steps of bipedalism, an adaptation perhaps driven by the need to travel between scattered food sources or to see over tall grasses. These early hominins were not yet human but marked a decisive departure from the strictly arboreal life of their ancestors. Their existence tells us that climate and habitat can shape the very architecture of our bodies, pressing evolution toward paths that seem improbable until they occur. The Neogene was not without its own extinctions. Many mammal lineages that flourished early in the epoch dwindled by its end, unable to adapt to harsher climates or competition with more specialised rivals. Yet unlike the cataclysmic endings of earlier periods, these extinctions were slower, spread across millions of years, and tied closely to gradual shifts in vegetation and climate. This rhythm of turnover built resilience into ecosystems, producing communities increasingly like those we see today. The haunting question of the Neogene is whether the emergence of hominins was inevitable or a contingency of circumstance. Did grasslands and cooling climates make upright walking unavoidable, or was it a rare evolutionary gamble that happened to succeed? We cannot answer with certainty. What we can say is that in the Neogene, Earth's landscapes came to resemble our own, and in their shifting patterns, they offered our ancestors both opportunities and perils. It is here, in the dance of grass, ice and restless continents, that the stage was set for us to appear. Another transformation of the Neogene lies in the realm of sound and sight. Subtler than the rise of grasslands, but just as profound. Fossils and genetic studies suggest that songbirds diversified dramatically during this time. Their calls, once simple, began to fill forests and open landscapes with complex melodies. Birdsong became a tool of territory and attraction, shaping ecological interactions and even altering plant dispersal patterns, as birds carried seeds farther and wider than wind alone could manage. At the same time, many mammals refined their sensory worlds. The open plains selected for sharper eyesight, longer range hearing, and improved coordination between herds. These abilities were not simply biological quirks, but strategies for survival in environments where visibility and vigilance meant the difference between life and death. The Neogene also redefined the chemistry of the atmosphere and oceans. As grasses spread, they altered carbon cycles in surprising ways. Their deep, fibrous roots locked carbon into soils, while the silica in their tissues created new abrasive food webs. Animals that grazed on these plants wore down their teeth more quickly, but the plants also pulled carbon from the air more efficiently than forests in some regions. Ocean chemistry shifted as well, influenced by weathering from rising mountain ranges like the Himalayas and Andes. Increased erosion delivered minerals into the seas, fueling plankton blooms that in turn supported expanding marine life. The Neogene shows us how the rise of something as unassuming as a blade of grass could ripple outward to affect global carbon balances and long-term climate. Meanwhile, the continents continued their slow dance. In the late Miocene and into the Pliocene, the African plate pressed northward, closing the Tethys Sea and creating the Mediterranean basin. At one point, about 6 million years ago, the Mediterranean nearly dried out in what geologists call the Messinian salinity crisis, leaving vast salt deposits across the basin. Later, when Atlantic waters returned, the sea was refilled in a catastrophic flood that carved channels still visible today beneath the Strait of Gibraltar. These dramatic changes influenced migration corridors and climates, reminding us that oceans and land were constantly reshaping the routes available for life. By the close of the Neogene, Earth looked startlingly modern, yet it was also a planet in tension, swinging between warmth and the first hints of the ice ages to come. The spread of hominins in Africa occurred in lockstep with these fluctuations, suggesting that the push and pull of climate may have nudged our ancestors toward adaptability and innovation. If the Neogene asks us how modern ecosystems emerged, its answer is layered, through grasses reshaping soils, mountains altering skies, seas drying and flooding, and primates venturing into new ways of living. It leaves us with a question that still lingers. When landscapes shift beneath you, do you cling to the old ways or take the first fragile step into the unknown? What does it mean to live in the blink of Earth's eye? To understand this, we enter the Quaternary, the span of just the last 2.5 million years. For a planet more than 4.5 billion years old, this period is less than a breath, yet it contains the story most relevant to us, the waxing and waning of ice, the rise and fall of great beasts, and the appearance of a species that named itself Homo sapiens. If all of Earth's history were compressed into a single calendar year, the Quaternary would begin only in the last day of December, and our written history would unfold in the final minutes before midnight. This disproportionate brevity should make us humble. We are newcomers in a world that has spun through unimaginable transformations long before we arrived. The Quaternary is defined by its ice ages. Unlike earlier times when Earth was entirely locked in snowball conditions or basked in greenhouse warmth, this epoch is marked by cycles, glacial and interglacial rhythms paced by variations in Earth's orbit and tilt. Sheets of ice advanced from the poles, covering much of North America, Europe and Asia, then retreated again, over and over, dozens of times. Each glacial maximum lasted tens of thousands of years, shaping landscapes through grinding, scraping and deposition. Valleys were carved into U-shapes, lakes gouged into basins, and entire regions transformed into tundra. During interglacials like the one we live in now, warmth returned, forests spread northward, and sea levels rose, drowning coastal plains. The climate shifts of the Quaternary made life a constant negotiation. Megafauna adapted to the cold. Mammoths and mastodons with shaggy coats, woolly rhinoceroses, giant ground sloths, and cave lions thrived in the open steppe tundra ecosystems. These environments, often called the Mammoth Steppe, stretched from Spain across Siberia to Alaska, forming the richest biomass of large animals the world has ever seen. In warmer interludes, other faunas took the stage. Elephants, hippos, and great antelope herds populated lush plains, while rainforests returned to the tropics. Evolution did not slow down. It sped up, producing species tuned to the rapid climate oscillations that characterize these 2.5 million years. It is in this restless setting that our own genus emerged. Fossils show Homo habilis crafting stone tools more than 2 million years ago in Africa. By 1.5 million years ago, Homo erectus strode out of Africa, spreading into Asia and Europe, wielding fire and hand axes. These early humans were not yet us, but they had taken a decisive step toward planetary dispersal. Over hundreds of thousands of years, other hominin species evolved and spread: Homo heidelbergensis, Homo neanderthalensis, Homo floresiensis, and many more, each adapting to local climates, each representing another branch of a tree that kept trying new forms. Only late in the Quaternary does Homo sapiens appear, somewhere between 300,000 and 200,000 years ago. Our species' rise coincided with one of the most volatile climatic intervals of the Quaternary. The last 100,000 years saw abrupt temperature swings recorded in ice cores from Greenland and Antarctica. In a few decades, regions could shift from warm to glacial conditions or back again. This instability may have pressured human groups to innovate, to develop complex tools, symbolic communication, and social networks robust enough to endure crisis. Around 70,000 years ago, Homo sapiens left Africa again, spreading across Eurasia, encountering other hominins, and eventually reaching Australia, the Americas, and remote Pacific islands. By the end of the Pleistocene, humans had established themselves as a global species, even as the Ice Age megafauna dwindled. The extinction of these great animals remains one of the haunting stories of the Quaternary. In North America, mammoths, saber-toothed cats, and giant ground sloths vanished around the time humans arrived. In Australia, enormous marsupial predators and giant kangaroos disappeared soon after human colonization. In Eurasia, woolly rhinoceroses and cave bears faded from the record as human populations spread. The causes are debated: climate stress, human hunting, or a synergy of both. But the result was the same. Ecosystems lost their giants, and humans became the dominant force shaping animal communities. The Quaternary is not only about ice and extinctions, it is also about the landscapes we know today. The Great Lakes of North America, the fjords of Norway, and the fertile lower soils of China all trace their origins to glacial action. Rivers shifted courses as ice sheets dammed and released floods, sometimes producing cataclysms that scoured landscapes in days. Sea levels fluctuated by more than 100 meters, exposing land bridges that humans and animals used to migrate. The Bering Land Bridge connected Asia and North America, while low sea levels in Southeast Asia allowed passage into Australia. These shifting corridors are part of why we find humans on every continent today. The haunting question of the Quaternary is what it means to live in a geological moment so brief, yet so decisive. We are shaped by climates that swung wildly, by landscapes carved by ice, and by animals that shared the planet until very recently. The Holocene, the current warm interval beginning about 11,000 years ago, has given us agriculture, cities, and civilization, but it is only one more interglacial in a long series. From the planet's perspective, it is temporary. Whether the future brings another ice age, or whether human activity has altered the cycle beyond recognition, remains uncertain. The Quaternary teaches us that stability is an illusion. The world has shifted dramatically within timeframes our ancestors could witness, and it will shift again. To live in the blink of Earth's eye is to inhabit a fragile equilibrium where glaciers, forests, oceans, and species, including us, are bound together in constant motion. The real question is not whether change will come, but how we will adapt when it does, just as every creature before us has had to adapt to the rhythm of ice and thaw. What does it mean to live in the blink of Earth's eye? To understand this, we enter the Quaternary, the span of just the last 2.5 million years. For a planet more than 4.5 billion years old, this period is less than a breath, yet it contains the story most relevant to us: the waxing and waning of ice, the rise and fall of great beasts, and the appearance of a species that named itself Homo sapiens. If all of Earth's history were compressed into a single calendar year, the Quaternary would begin only in the last day of December, and our written history would unfold in the final minutes before midnight. This disproportionate brevity should make us humble. We are newcomers in a world that has spun through unimaginable transformations long before we arrived. The Quaternary is defined by its ice ages. Unlike earlier times when Earth was entirely locked in snowball conditions or basked in greenhouse warmth, this epoch is marked by cycles, glacial and interglacial rhythms paced by variations in Earth's orbit and tilt. Sheets of ice advanced from the poles, covering much of North America, Europe and Asia, then retreated again, over and over, dozens of times. Each glacial maximum lasted tens of thousands of years, shaping landscapes through grinding, scraping and deposition. Valleys were carved into U-shapes, lakes gouged into basins, and entire regions transformed into tundra. During interglacials like the one we live in now, warmth returned, forests spread northward, and sea levels rose, drowning coastal plains. The climate shifts of the Quaternary made life a constant negotiation. Megafauna adapted to the cold. Mammoths and mastodons with shaggy coats, woolly rhinoceroses, giant ground sloths, and cave lions thrived in the open steppe tundra ecosystems. These environments, often called the Mammoth Steppe, stretched from Spain across Siberia to Alaska, forming the richest biomass of large animals the world has ever seen. In warmer interludes, other faunas took the stage. Elephants, hippos, and great antelope herds populated lush plains, while rainforests returned to the tropics. Evolution did not slow down. It sped up, producing species tuned to the rapid climate oscillations that characterized these 2.5 million years. It is in this restless setting that our own genus emerged. Fossils show Homo habilis crafting stone tools more than 2 million years ago in Africa. By 1.5 million years ago, Homo erectus strode out of Africa, spreading into Asia and Europe, wielding fire and hand axes. These early humans were not yet us, but they had taken a decisive step toward planetary dispersal. Over hundreds of thousands of years, other hominin species evolved and spread. Homo heidelbergensis, Homo neanderthalensis, Homo floresiensis, and many more, each adapting to local climates, each representing another branch of a tree that kept trying new forms. Only late in the Quaternary does Homo sapiens appear, somewhere between 300,000 and 200,000 years ago. Our species' rise coincided with one of the most volatile climatic intervals of the Quaternary. The last 100,000 years saw abrupt temperature swings recorded in ice cores from Greenland and Antarctica. In a few decades, regions could shift from warm to glacial conditions or back again. This instability may have pressured human groups to innovate, to develop complex tools, symbolic communication, and social networks robust enough to endure crisis. Around 70,000 years ago, Homo sapiens left Africa again, spreading across Eurasia, encountering other hominins, and eventually reaching Australia, the Americas, and remote Pacific islands. By the end of the Pleistocene, humans had established themselves as a global species, even as the Ice Age megafauna dwindled. The extinction of these great animals remains one of the haunting stories of the Quaternary. In North America, mammoths, saber-toothed cats, and giant ground sloths vanished around the time humans arrived. In Australia, enormous marsupial predators and giant kangaroos disappeared soon after human colonization. In Eurasia, woolly rhinoceroses and cave bears faded from the record as human population spread. The causes are debated: climate stress, human hunting, or a synergy of both, but the result was the same. Ecosystems lost their giants, and humans became the dominant force shaping animal communities. The Quaternary is not only about ice and extinctions, it is also about the landscapes we know today. The Great Lakes of North America, the fjords of Norway, and the fertile loose soils of China all trace their origins to glacial action. Rivers shifted courses as ice sheets dammed and released floods, sometimes producing cataclysms that scoured landscapes in days. Sea levels fluctuated by more than 100 meters, exposing land bridges that humans and animals used to migrate. The Bering Land Bridge connected Asia and North America, while low sea levels in Southeast Asia allowed passage into Australia. These shifting corridors are part of why we find humans on every continent today. The haunting question of the Quaternary is what it means to live in a geological moment so brief, yet so decisive. We are shaped by climates that swung wildly, by landscapes carved by ice, and by animals that shared the planet until very recently. The Holocene, the current warm interval beginning about 11,000 years ago, has given us agriculture, cities, and civilization. but it is only one more interglacial in a long series. From the planet's perspective, it is temporary. Whether the future brings another ice age, or whether human activity has altered the cycle beyond recognition, remains uncertain. The Quaternary teaches us that stability is an illusion. The world has shifted dramatically within time frames our ancestors could witness, and it will shift again. To live in the blink of Earth's eye is to inhabit a fragile equilibrium, where glaciers, forests, oceans and species, including us, are bound together in constant motion. The real question is not whether change will come, but how we will adapt when it does, just as every creature before us has had to adapt to the rhythm of ice and thaw. What does it mean that Earth is ancient and we are new? To stand at the end of this 4.5 billion year story is to feel small, fragile, and at the same time unbearably present. The Earth has survived bombardments of stone from space, global ice sheets, volcanic cataclysms, and extinctions so severe they erased nearly all life. Across its surface, continents have split and collided, mountains have risen and been ground down, and oceans have appeared and vanished. Life has endured and transformed with each shift. Compared to this immensity, our own existence is but a sliver, measured not in hundreds of millions of years, but in thousands, not in epochs, but in lifetimes. And yet here we are, speaking into the silence of deep time, trying to make sense of a story that is still unfolding. The fragility of the present becomes clear when we consider how many lineages never made it this far. The trilobites, once rulers of Cambrian seas, gone. The ammonites, survivors of hundreds of millions of years, gone. The mammoths, which grazed the tundras only yesterday in geological terms, gone. The Earth does not guarantee continuity to any species. Even the longest survivors, cyanobacteria, sharks, crocodiles, have shifted, adapted, and yielded to change. Our own appearance, so recent it hardly registers against the backdrop of deep time, is not an assurance of permanence. It is instead a reminder that the ground beneath our feet is temporary, that the ecological balances we depend on are the outcome of long histories we barely understand. What is striking is not only how short our existence is, but how much we depend on the rare stability of this moment. The Holocene climate, which allowed agriculture and civilization, is an exception, not the rule. For most of the Quaternary, Earth swung between extremes of ice and warmth. For most of the Phanerozoic, climates were hotter and seas higher than anything we have experienced. For most of its existence, Earth was a planet of microbes, not of mammals. The present feels normal to us, only because it is all we have known. In the wider history of the planet, it is abnormal, a lucky accident of orbital mechanics and atmospheric chemistry. And so, we face a haunting question. What will future layers of rock say about us? If geologists tens of millions of years from now were to dig into sediments, would they find traces of our plastics, our concrete, our isotopes, our extinctions? Would they see a brief bright layer marking the Anthropocene, gone as quickly as it came, or a longer record of adaptation and survival? We cannot know. All we can do is recognise that for the first time in Earth's history, a species is aware of deep time, aware of its place in the stratigraphy of the planet. Awareness itself is unprecedented. Whether it changes the outcome remains uncertain. There is comfort in the scale of deep time. Whatever storms we face, the Earth will continue. Continents will drift, mountains will rise, oceans will open and close. The sun itself will evolve, brightening slowly, eventually making the Earth uninhabitable in a distant future billions of years away. Against this inevitability, human crises shrink. Yet this is not a reason for apathy. It is precisely because our time is short that it matters. For our descendants, whether a few centuries or many millennia from now, the decisions we make about how to live on this planet may determine whether they inherit a flourishing biosphere or a diminished one. Humility before deep time does not mean surrender, it means perspective. The stories of vanished lineages, of continents ground to dust, of oceans that came and went, remind us that we are not outside nature but woven into it. The molecules in our bones were forged in stars that exploded long before the Earth existed. The oxygen we breathe was first exhaled by cyanobacteria billions of years ago. The soils that feed us are the weathered remains of mountain chains older than our species, To live in the present is to live inside a history so vast that it stretches beyond imagination. Perhaps that is the greatest lesson of all. Earth is ancient. We are new. Our fragility is not a flaw, but a truth of our existence. To recognise it is to see clearly, to understand that life has never been guaranteed, and that meaning is not found in permanence but in participation. We are participants in a story billions of years old, inheritors of time carved into stone, and stewards, however briefly, of a living planet. What we leave behind will not be measured in decades or dynasties, but in the quiet testimony of rocks. And as we close this journey through Earth's history, the question remains, lingering like the echo of a glacier retreating or a volcano's last eruption. In this fragile present, what will we choose to become? You've just travelled 4.5 billion years in the span of a few hours, from molten beginnings to oceans of microbes, from forests of coal to herds of mammoths, from impact craters to quiet civilizations. We have seen how Earth has turned again and again through violence and renewal. And in all of that, the piece that is ours, the part we call history, barely registers. A few minutes before midnight on the geological clock, a blink of an eye in deep time. This is a channel for soft science, not wild speculation. We do not have all the answers, and much of what we've said is still debated, still being tested, still unfolding in new discoveries. That humility is part of the story. The rock record does not tell us everything, but it tells us enough to see how fragile the present really is, and how astonishing it is that we exist at all. If you happen to drift off during some of the chapters, that's all right. I put timestamps in the description so you can pick up where you left off the next day. The whole story, from beginning to end, is worth it. And whether you listened while cooking, driving, working, or lying awake in the dark, thank you for joining this experiment in slow storytelling. If you appreciate this kind of long-form science, please take a moment to like and subscribe. It helps other people find this content, and it supports the making of calm, detailed explorations in a noisy world. Feel free to share in the comments how you use this, before sleep, on the road, in the shower, or with headphones at work. The diversity of those answers always makes this project feel more alive. And as always, stay curious, stay calm. I'll see you in the next story.